If you could peer deep into the constellation Pegasus, through the veil of night and beyond the reach of the unaided eye, you'd find a glowing spiral suspended in the void. It stretches over 120,000 light-years, spinning in silent elegance, its arms laced with stars, dust, and gas. At first glance, it might seem strangely familiar. The structure is unmistakably spiral. A central bulge gleams with densely packed stars. Dust lanes ripple through the disk. It looks almost exactly like the Milky Way, as though you're seeing a mirror of our home galaxy from a vantage point we could never physically achieve. But before we continue, subscribe to the channel and like the video. But look closer, and the illusion begins to unravel. Something about the movement isn't quite right. Beneath its resemblance to the Milky Way, this galaxy hides a twist. Its central bulge is spinning far faster than expected. It's a quiet rebellion against the norms of galactic behavior. It challenges the models, mocks the assumptions, and opens a door to cosmic questions that remain unresolved. This is NGC 7331, a galaxy so similar to ours that astronomers often call it our galactic twin. Yet, as in all good twin stories, there's a key difference, one that may alter everything we think we know about galactic dynamics. NGC 7331 is no ordinary spiral galaxy. It's a cosmic paradox, familiar in form yet strange in behavior. Structurally, it mirrors the Milky Way with its sweeping arms and bright core, and yet, that very core defies the rules. It spins with a ferocity unseen in galaxies of its type. While most galactic bulges rotate slowly, weighed down by age and mass, NGC 7331's bulge defies this with speed, as though driven by some hidden force or shaped by a forgotten history. Why is this important? Because we can't observe our own galaxy from the outside. We're trapped inside the Milky Way, surrounded by its dust and stars, unable to see its full structure. So we look outward, to galaxies like NGC 7331, not just for comparison, but for revelation. Studying NGC 7331 is like looking into a cosmic mirror that reflects our form, but maybe not our fate. In this twin galaxy, we find more than similarity, we find mystery. What does it mean when something looks like home but behaves like a stranger? Could the Milky Way harbor similar surprises, hidden behind our observational limitations? Could its bulge be spinning faster than we think? Or does NGC 7331 represent a divergent evolutionary path, a fork in the spiral road? NGC 7331 isn't famous like Andromeda or dazzling like the Whirlpool Galaxy. But what it lacks in popularity, it makes up for in depth. It's a galaxy that reflects, reveals, and resists simplicity. As we dive into its history, structure, and secrets, we're not just exploring a distant collection of stars. We're exploring a possibility. That the familiar, in the vastness of the cosmos, always holds a twist. In the late 18th century, long before modern space telescopes or digital imaging, the sky was still a largely uncharted realm. It was during this time, specifically in 1784, that the prolific astronomer William Herschel turned his handcrafted telescope toward the constellation Pegasus. Among the countless celestial objects he catalogued, one faint, hazy patch of light stood out. It didn't twinkle like a star. It had no sharp edges or defined contours. It was ghostly, elliptical, and ethereal. Herschel, unaware of its true nature, recorded this luminous smudge as part of his growing list of nebulae, an ever-expanding record of deep sky mysteries. Centuries later, what Herschel had seen would be identified not as a nebula within our galaxy, but as a galaxy in its own right, far, far beyond the Milky Way. That patch of light became known as NGC 7331, and its true significance began to emerge as technology caught up with imagination. It took time for humanity to accept the radical idea that some of these nebulae were actually entire galaxies, vast star systems like our own, scattered throughout the cosmos. Today, we know that NGC 7331 is located approximately 40 million light-years from Earth, meaning the light that reaches us now began its journey long before humanity even understood the scale of the universe. To grasp what that distance implies, imagine the entire timeline of human civilization compressed into a single breath. Now imagine that breath traveling through space for 40 million years before arriving at our instruments. What we see is not what is, but what was. Its location in the constellation Pegasus makes it a target that is conveniently visible from the northern hemisphere during autumn months. Under dark skies with a decent amateur telescope, it becomes accessible to dedicated stargazers. It doesn't blaze with brilliance, but its soft, extended glow carries with it a quiet majesty, a visual whisper of its immense size and staggering distance. Its visibility and relative brightness among nearby galaxies contributed to its early documentation, but it wasn't until the 20th century that astronomers began to understand its structure and dynamics. What once appeared as a faint blur gradually became recognized as a massive spiral system, eerily similar to the Milky Way. Its discovery thus bridges two eras of astronomical thought: the age of speculation and the age of cosmic understanding. NGC 7331's position on the celestial sphere also holds a curious twist. From our perspective, it seems to lead a collection of smaller galaxies nearby in the sky. This apparent grouping later sparked interest not just for its scientific value, but for the illusions it created, alignments that suggest physical proximity, even when none exists. That visual arrangement would go on to be named the deerlick group, though, as we would eventually learn, most of the surrounding galaxies are far more distant than they appear. Still, NGC 7331 reigns visually at the center of this stellar stage, a foreground anchor among background players. In essence, the discovery of NGC 7331 was not just the identification of a bright object in Pegasus. It was an early step on the path to understanding galaxies as fundamental building blocks of the universe. Herschel's act of documentation, made through dimmed glass and candlelight, inadvertently opened a door into the vast spiral structures beyond our own. And now, centuries later, that same galaxy continues to challenge, inspire, and guide our exploration of the cosmos. To truly appreciate the majesty of NGC 7331, we need to consider its scale, a dimension so vast that even light, traveling at over 186,000 miles per second, takes more than 100,000 years to traverse it. Stretching an estimated 120,000 light-years across, NGC 7331 is a colossal spiral structure. That places it slightly larger than our own Milky Way, which spans roughly 100,000 to 105,000 light-years from tip to tip. Those size comparisons among galaxies are never exact, especially due to differing definitions of where a galaxy ends. NGC 7331 clearly stands among the giants in our cosmic neighborhood. Its sheer breadth means it holds hundreds of billions of stars, perhaps even more than the Milky Way. If you were to stand on a planet orbiting a sun-like star deep within one of its spiral arms, the sky would likely be ablaze with stars. The galactic disk would stretch from horizon to horizon like a river of diamonds, and the dense central bulge would glow in the night like a pale, concentrated sunrise. NGC 7331's mass also matches its size. Estimates suggest it harbors a mass on par with, or even exceeding, the Milky Way's total mass, which is in the range of 1 to 2 trillion solar masses when dark matter is included. Its gravitational hold is immense, shaping the orbits of stars and gas clouds over tens of thousands of light-years, generating the cohesive spiral structure we admire from afar. But size isn't just about breadth, it's also about luminosity. NGC 7331 shines brightly in the sky, not in the way stars do, but as a diffuse, extended glow. Its brightness in visible light is substantial enough to make it a favorite among amateur astronomers. It's one of the brightest galaxies and it's part of the sky, a beacon in the deep, dark ocean of intergalactic space. That brightness is due not only to its vast population of stars but also to the abundance of young, blue stars burning intensely in its spiral arms. These hot, short-lived stars contribute significantly to the galaxy's overall luminosity. What makes this particularly compelling is that despite being 40 million light-years away, a staggering distance, NGC 7331 still stands out. Many galaxies become mere shadows at such distances, but this one maintains its visual impact, thanks in part to its scale, structure, and orientation. It's not just wide, it's brilliant, active, and massive. Its scale also makes it an ideal target for large-scale surveys and high-resolution imaging. Telescopes like the Hubble Space Telescope and various radio and infrared observatories have all turned their gaze toward NGC 7331 to examine it in detail. Each time they do, they peel back another layer of its complexity, from the fine threads of its spiral arms to the dense concentration of stars in its bulge. The bigger the galaxy, the more stories it holds, and NGC 7331 has had billions of years to write its cosmic epic. As one of the brighter and larger spiral galaxies in our celestial neighborhood, it provides a crucial benchmark. When astronomers study the evolution of spirals, how they form, grow, rotate, and age, NGC 7331 often finds its place among the reference examples. It is not a faint whisper lost in the background of the universe. It is a clear, distinct voice, a structure grand enough to rival our own home and luminous enough to be heard across the intergalactic void. NGC 7331 presents itself as a magnificent archetype of spiral galaxy formation, a celestial canvas painted with swirling arms, star-studded dust lanes, and a glowing central bulge that radiates the accumulated starlight of billions of suns. When astronomers first began to classify galaxies systematically in the 20th century, they needed a way to sort the chaotic variety of galactic shapes and structures into something orderly and comprehensible. The system that eventually took hold was the Hubble sequence, often visualized as a tuning fork diagram. In that classification, NGC 7331 falls into the category SA-SB, making it an unbarred spiral galaxy with moderately wound arms and a prominent central bulge. This designation is more than a label, it's a reflection of the physical and dynamic architecture of the galaxy. The SA indicates a spiral galaxy that lacks a central bar, a defining trait we'll explore more deeply soon. The S suggests that the spiral arms originate directly from the nucleus or bulge, rather than from a ring, and the B denotes the tightness of those arms, midway between the tightly wound spirals of an A-type and the loose, open spirals of a C-type. In this way, NGC 7331 is a classic example of balanced spiral architecture, not too tightly bound, not too flung apart, just orderly enough to exhibit grace, yet dynamic enough to stir intrigue. When seen through modern telescopes, NGC 7331 reveals a layered beauty. Its majestic spiral arms sweep outward in vast, symmetric arcs, stretching through the disk like tendrils of starlight. These arms are laced with glowing regions of star formation, nurseries where hot, young stars ignite in brilliant clusters. Dust lanes thread through them, darkening sections of the spiral in intricate patterns, each filament a signature of cold interstellar gas poised to become the next generation of stars. These lanes are particularly rich in molecular hydrogen and other cool elements, the raw ingredients for stellar creation. The structure of NGC's 7,331 spiral arms, particularly when viewed in optical and near-infrared wavelengths, appears remarkably well-defined. The arms don't fragment easily or lose coherence as they move outward, suggesting that the underlying gravitational potential of the disk is stable and massive. This is a galaxy that has, for the most part, avoided major disruptive events in recent cosmic history, such as large collisions or tidal shredding by neighboring giants, that would typically distort or tangle spiral arms. That relative calm allows its features to retain symmetry and elegance. Then there's the luminous bulge, the spherical or football-shaped glow at the galaxy's heart. This region consists primarily of older, redder stars, stellar elders that formed early in the galaxy's life. In NGC 7331, this bulge is particularly prominent and dense, dominating the central region both visually and gravitationally. Unlike the blue-white light of hot, young stars in the arms, the bulge's light has a warm, golden tone, a sign of ancient suns that have long since left behind the frenzied activity of youth. In fact, this luminous bulge serves as a major point of resemblance to our own Milky Way. Both galaxies possess prominent central bulges, with populations of old stars likely exceeding several billion years in age. The sheer density of the bulge means stars are packed closely together, on average, much closer than in the solar neighborhood. Within a single cubic light-year, there could be thousands of stars. It's a region not only of intense stellar concentration but also of complex orbital dynamics, where stars move in tightly bound, often elliptical orbits under the immense gravitational pull of the Bulge's mass and, possibly, a supermassive black hole lurking at its center. Despite its similarity to the Milky Way, there are key distinctions. NGC 7331 lacks a bar structure, a feature our own galaxy possesses. In barred spiral galaxies, the central bulge is bisected by an elongated bar of stars and gas, believed to play a role in channeling material inward and driving star formation near the core. The absence of this bar in NGC 7331 implies differences in the internal flow of matter, as well as variations in how the bulge and disk exchange angular momentum over time. Some theories suggest that bars form as galaxies mature or interact with companions, and their absence may hint at a more isolated or stable evolutionary path. This makes NGC 7331 particularly valuable for comparison. By contrasting a barred spiral, like the Milky Way, with an unbarred one, like NGC 7331, astronomers can explore how such internal features affect a galaxy's structure, star formation rates, and long-term evolution. The morphology of NGC 7331, its shape and appearance, becomes even more fascinating when examined across different wavelengths of light. In ultraviolet, we see the fingerprints of newly minted stars and the blaze of recent star-forming regions in the spiral arms. In visible light, the galaxy glows with a mix of stellar populations, blue hues tracing younger stars, and golden tones reflecting the old. In infrared, dust structures become more visible, revealing colder, obscured regions where stars are just beginning to form. In radio and submillimeter wavelengths, vast reservoirs of hydrogen gas are mapped, essentially, the fuel tanks for the galaxy's future generations of stars. This multi-wavelength picture reinforces NGC 7331's status as a living galaxy, not static or fossilized, but vibrant and dynamic. Star formation continues, particularly in the spiral arms, where density waves compress gas and trigger bursts of stellar birth. Dust swirls through the disk, tracing past events and future possibilities. The entire system rotates, ever so slowly, around its massive center, each star contributing to a grand ballet that spans tens of thousands of light years. This is what makes NGC 7331 such a compelling object of study. It doesn't just resemble the Milky Way, it encapsulates a critical stage of galactic development. Its features suggest maturity, order, and sustainability. It has the classic appearance of a spiral galaxy that has evolved gracefully, without catastrophic interruptions. And yet, beneath that calm appearance lies a secret, a fast-spinning bulge, an anomaly that stands in sharp contrast to the smooth elegance of its spiral arms. When astronomers look at NGC 7331, they don't just see beauty. They see a model, a template, a living example of what spiral galaxies are, and what they might become. It's a galaxy that challenges our understanding, not through chaos or violence, but through subtle difference. And as we gaze at its spiral arms, winding outward from a glowing core, we are reminded that even familiar forms can contain the unexpected. In the grand architecture of spiral galaxies, the presence, or absence, of a central bar is more than just a visual detail. It's a defining characteristic that can shape the entire life cycle of a galaxy. The Milky Way, for instance, has a pronounced bar, a thick, elongated structure of stars that stretches through its central bulge and acts almost like a cosmic conveyor belt, shuttling gas inward to fuel star formation near the core. But NGC 7331 follows a different blueprint. It is what astronomers classify as unbarred, a structural variation that places it into a fundamentally distinct evolutionary pathway. When we say that NGC 7331 is unbarred, we mean that its spiral arms emerge directly from its luminous central bulge, not from the ends of a bar-like structure as in barred spirals. This distinction is embedded right in its classification, SA-SB, the SA, denoting that it is a spiral galaxy without a central bar. Visually, this means its arms appear to curve outward in a more symmetric and graceful fashion, flowing from the edges of the bulge like the petals of a blooming flower rather than being funneled from the ends of a straight bar. But structurally, the implications go much deeper than aesthetics. Bars in spiral galaxies are thought to be transient features that arise from gravitational instabilities within the disk. Over cosmic timescales, they form, evolve, and sometimes dissolve. They're not mere ornaments. They play active roles in galactic evolution. For instance, they drive the inflow of gas toward the galactic center, feeding central star formation and, potentially, the growth of a supermassive black hole. In barred galaxies, this mechanism helps maintain a dynamic cycle of material redistribution that shapes the development of the inner disk and bulge. In the case of NGC 7331, the lack of a bar suggests a different kind of internal dynamics. The gas and stars in its disk orbit more symmetrically around the galactic center, without being channeled inward by a stellar bar. This could mean that central star formation occurs at a different pace, or in different locations, compared to a barred galaxy. Without the gravitational torque of a bar structure, gas in NGC 7331 likely remains distributed more evenly across its disk, rather than piling up near the core. This may result in a slower or more sustained mode of star formation, and possibly a more stable overall structure. What's especially fascinating is that unbarred spirals like NGC 7331 are not necessarily less evolved. In fact, bars are more common in the current universe. Roughly 2/3 of spiral galaxies have some form of a central bar. This has led to the idea that many spirals develop bars as they age. If that's true, then NGC 7331 might represent an earlier or alternate phase of galactic evolution, or it may have avoided bar formation altogether due to differences in mass distribution, rotational speed, or environmental factors. Alternatively, it could have had a bar in the distant past that dissolved over time. Galaxies are not static, and their structures can shift subtly or dramatically over billions of years. There are other possible reasons NGC 7331 remains unbarred. One theory suggests that galaxies with especially massive bulges, like NGC 7331, may resist the formation of bars because the gravitational influence of the bulge stabilizes the inner disk. If the bulge is dominant enough, it can suppress the kinds of instabilities that typically lead to bar formation. This idea is consistent with the prominent, fast-rotating bulge at the heart of NGC 7331, a feature that is not only bright and massive but also dynamically unusual. From an observational standpoint, the absence of a bar allows us to study the galaxy's spiral arm dynamics in a purer form. Without the complicating influence of a bar driving radial flows of gas, the arms of NGC 7331 may represent more natural responses to the gravitational potential of the disk. These arms appear to emerge directly from the bulge and curve outward in symmetrical, moderately wound spirals. They contain an abundance of star-forming regions, clusters, and nebulae, which can be examined without the confounding effects of bar-driven shocks or compression. For astronomers trying to understand the diversity of spiral galaxies, unbarred spirals like NGC 7331 serve as a crucial counterpoint. By comparing them to barred spirals like our own, researchers can tease apart the roles bars play in galactic metabolism, how they affect the flow of material, the distribution of stars, the formation of bulges, and even the evolution of dark matter halos. Another consequence of NGC 7331's unbarred nature is how it influences galactic rotation patterns. In barred galaxies, the bar often rotates as a rigid structure, creating resonance zones where stars and gas respond to the bar's gravitational rhythm. These resonances can shape star formation rings and affect orbital paths in complex ways. NGC 7331, lacking a bar, may have a smoother rotational profile near its center, which makes its anomalously fast-spinning bulge even more surprising. Without a bar to transfer angular momentum or torque the inner regions, the rapid rotation of the bulge becomes harder to explain. It stands as an outlier in an otherwise orderly structure. What we're left with is a galaxy that both conforms to and defies expectations. It follows the classic blueprint of a mid-type spiral galaxy: elegant arms, a dominant bulge, a disk rich with star-forming material, but skips one of the most common galactic components, the bar. In doing so, it opens a window into a different kind of galactic life. One where evolution followed another road. one where the symmetry of formation remained largely undisturbed. One that may help us understand what our own Milky Way once was, or what it might yet become, should its bar fade with time. NGC 7331 teaches us that not all spirals spiral the same way. Structure is destiny, but only to a point. Just as humans can share similar DNA but live entirely different lives, galaxies can share classifications but follow radically divergent paths. And somewhere within that divergence, we find meaning, not only about how galaxies form and age, but about the possibilities of cosmic diversity itself. When we observe galaxies in the universe, our perspective, our viewing angle, can significantly shape what we learn. Some galaxies present themselves edge-on, appearing as razor-thin streaks of light, concealing much of their internal structure while revealing the vertical distribution of stars and dust. Others lie face-on, like a perfect spiral painted on a canvas, offering breathtaking views of their arms and core but little information about their three-dimensional thickness. NGC 7331 offers something rare and especially valuable, an intermediate orientation, tilted just enough to reveal both depth and detail. It is not face-on, nor is it edge-on. It hangs in space at a gentle incline, letting us gaze into its rotating disk while simultaneously peering through layers of gas, dust, and stars stacked upon each other. This inclination is estimated to be about 74 degrees, just shy of completely edge-on. This angle turns out to be an astronomer's gift. It provides a near-ideal view for studying the galaxy's structural components without the limitations imposed by extreme orientations. When a galaxy is seen edge-on, dust lanes and bulges are often silhouetted dramatically, but much of the spiral structure is lost to overlapping light. When it's viewed face-on, spiral patterns are exquisitely revealed, but we lose the sense of vertical layering and disk thickness. NGC 7331's intermediate tilt grants a hybrid perspective. We can trace the winding spiral arms as they arc outward from the luminous bulge, while also perceiving the vertical stratification of stars and gas in the disk. From this vantage point, the spiral arms of NGC 7331 appear layered and stacked, giving us a rich cross-section of galactic behavior. We see young blue stars forming in active star-forming regions near the arms, dark dust lanes crossing the disk in jagged strokes, and older, redder stars glowing softly above and below the galactic plane. This enables astronomers to study how different stellar populations are distributed, not just across the galaxy, but within it. Younger stars tend to hug the midplane, embedded in the dense, gas-rich spiral arms, while older populations are puffed up into a thicker disk or halo. Observing these layers from a slant angle allows scientists to disentangle light contributions from each population and build a three-dimensional map of stellar distribution. This particular angle also gives us a clearer view of the galactic bulge, the central region of the galaxy, swollen with densely packed stars and possibly home to a supermassive black hole. If NGC 7331 were face-on, the bulge might be partially hidden behind the glare of foreground stars and active star-forming regions. If it were edge-on, it would merge with the disk and become harder to isolate. But at 74 degrees, the bulge stands out cleanly, glowing like a beacon at the galaxy's core. The light from this bulge is layered behind and against the swirling patterns of the disk, allowing astronomers to study not only its brightness and shape but also its kinematics, how it rotates, how fast, and in what direction compared to the rest of the galaxy. Spectroscopic studies leverage this tilt to map the rotation curve of NGC 7331, measuring how quickly stars and gas move as a function of distance from the center. The angle is just shallow enough that Doppler shifts in light from approaching and receding sides of the disk are easily detectable. These rotational velocities help confirm the presence of dark matter in the galaxy by showing that outer stars orbit far faster than visible mass alone would allow. Without the perfect inclination, such measurements would be muddled, too face-on, and there would be little measurable velocity along our line of sight. Too edge-on and overlapping light sources would blur velocity readings. NGC 7331, by pure cosmic fortune, lands in the sweet spot. In this tilted position, dust lanes also become strikingly visible. Dust in spiral galaxies often clumps into vast, complex lanes that absorb and scatter visible light. When seen face-on, These lanes are flat patterns, like smudges on a chalkboard. But from a slanted perspective, they gain depth and shadow, revealing their vertical thickness and giving insight into the density and distribution of interstellar material. In NGC 7331, we can follow these lanes as they slice diagonally across the disk, tracing the spiral arms and hinting at regions rich with molecular gas. These are the birthplaces of stars, the raw, cold nurseries where gravity is still sculpting matter into new suns. By observing these structures at an angle, astronomers can better estimate the amount of obscured starlight, and by correcting for dust attenuation, reconstruct the galaxy's true luminosity profile. The orientation also aids our understanding of how galactic warping might occur. Some spiral galaxies exhibit subtle or extreme warps in their outer disks, caused by gravitational interactions, internal instabilities, or the influence of dark matter halos. In NGC 7331's case, its disk appears relatively stable, but the tilt helps researchers test for small asymmetries, ripples in starlight or warps in gas flow, that might hint at past encounters or internal shifts. These minor features are often invisible in face-on systems, but become detectable when viewed from a slight angle. Additionally, this angle opens the door to polarimetric studies. By analyzing how light is polarized as it passes through different layers of gas and dust, astronomers can infer the magnetic field structure of the galaxy. The line-of-sight depth in NGC 7331 means that polarized light carries a three-dimensional record of the interstellar medium's properties, something again made possible by the galaxy's ideal orientation. From an observational standpoint, it's not an overstatement to say that NGC 7331 offers one of the most informative views of a Milky Way, like spiral, that we can observe. We're given the rare chance to see into the galaxy, not just across its face, but into its very depth. This spatial layering is what allows astronomers to build detailed 3D models of its components, to estimate the vertical thickness of its disk, to measure the height and radius of the bulge, to chart gas density gradients, and to understand how gravity shapes and maintains this spiraled order. This tilted view also imbues the galaxy with a particular kind of aesthetic majesty. To the eye, especially in long-exposure photographs, NGC 7331 looks like it's gliding across space, not lying flat like a coin, but rising like a celestial wave. The light spills out at angles, the arms stretch and fade into the cosmic sea, and the whole form looks more alive, more real, than a diagrammatic face-on galaxy. There is motion in its stance, and depth in its glow. And so, through this fortuitous inclination, NGC 7331 gives us the best of both worlds. A sweeping, nearly full view of its spiral form, coupled with a revealing glimpse into its layered interior. It's a vantage point that turns a simple observation into a multidimensional exploration. In many ways, it's like being able to view the Milky Way from just outside its rim, close enough to see the arms curve around, but at an angle that lets you dive into the disk and trace the pathways of stars and gas. In this sense, NGC 7331 becomes more than a distant galaxy. It becomes our stand-in, our observational proxy, our twin, but one we can finally view from the outside, tilted just right to unlock its secrets. At the heart of nearly every spiral galaxy lies a bulge, an ancient, glowing spheroid of stars packed so tightly that their combined light often overwhelms the core. These bulges are typically calm and slow-rotating compared to the dynamic disks that wrap around them. In most cases, the bulge behaves like a stellar memory, a quiet, massive relic of the galaxy's early years. It's where time slows, motion dulls, and stellar evolution plays out on ancient timelines. But NGC 7331 is no ordinary spiral, and its central bulge refuses to conform. Despite sharing the overall structure of the Milky Way, with spiraling arms, a luminous disk, and a central bulge, NGC 7331 diverges sharply when we look at how its bulge behaves. This isn't a passive, sluggish structure sitting at the galactic center. It rotates, and rotates quickly, far more so than astronomers would expect for a bulge of its size, mass, and classification. Instead of behaving like a spheroidal collection of largely randomized star orbits, as is typical for a bulge, NGC 7331's core spins with surprising vigor, outpacing even parts of its outer disk. This has become one of the most intriguing puzzles in the study of galactic dynamics. When scientists began measuring the rotational velocities of stars within the bulge using Doppler spectroscopy, they found that the stars were moving at speeds not typically associated with classical bulges. In most spiral galaxies, including the Milky Way, bulges are pressure-supported structures, meaning that random stellar motions and gravitational equilibrium maintain their shape and dynamics. They do rotate, but slowly, certainly more slowly than the disk. But in NGC 7331, the bulge appears to be rotation-supported, behaving more like a fast spinning wheel than a static central weight. The implications of this are profound. First, it forces a reconsideration of how bulges form and evolve. There are generally two main types of bulges identified in spiral galaxies: classical bulges and pseudobulges. Classical bulges form early through rapid, violent mergers, essentially galactic collisions that smash together star systems and create a rounded core supported by random motion. These bulges are old, dense, and relatively inert. Pseudobulges, on the other hand, are thought to form more gradually from internal processes within the galaxy, such as disk instabilities that drive gas inward, forming new stars and adding angular momentum. These tend to be flatter, younger, and more rotationally active. So where does NGC 7331's bulge fall? Its high rotation speed suggests it doesn't fit neatly into either category. It's too round and massive to be a classic pseudobulge, and too dynamic and fast to be a classical bulge. Instead, it might represent a hybrid structure, or even a third class altogether, perhaps a fast classical bulge, born from early mergers but later spun up by disk interactions or hidden internal processes. One possibility is that NGC 7331 experienced minor mergers or gravitational interactions in its past that deposited angular momentum into the bulge without significantly disturbing the rest of the galaxy's structure. Such events could have transferred momentum into the inner regions, causing the bulge to spin faster without warping the disk or arms. This kind of scenario is difficult to model, but it's becoming an increasingly plausible explanation as more galaxies are discovered with unusually fast cores. Another possibility involves the inflow of gas from the disk toward the core over cosmic time. If enough material has spiraled inward, particularly if channeled by subtle disk instabilities or spiral density waves, it might have gradually added rotational energy to the bulge. New stars formed from this inflowing gas could inherit the disk's angular momentum, creating a composite population: older, slower stars mixed with younger, faster rotating ones. The result would be a bulge that appears classically round but spins like a disk. Yet another consideration lies in the potential role of dark matter. If the central region of NGC 7331 is embedded in a dense dark matter concentration with a unique shape or orientation, it could influence the rotational dynamics of visible matter in ways that aren't fully understood. While dark matter itself doesn't emit or absorb light, its gravitational effects can subtly shape how stars move, and perhaps even accelerate or retard rotation in specific regions. Whatever the cause, the effect is clear. NGC 7331's bulge defies expectations, acting not like a sedentary anchor but a kinetic powerhouse. This has ripple effects throughout galactic research. When astronomers model the evolution of galaxies, they often rely on simulations that assume relatively passive bulges. NGC 7331 challenges those assumptions and suggests that bulges might be more dynamic than previously thought. In fact, the rotation of the bulge complicates the very act of observing and measuring the galaxy. Spectroscopic observations must account for the rapid movement of stars in the central region, disentangling overlapping light from foreground disk stars and background halo stars. Velocity dispersion measurements, the spread of speeds at which stars move, are affected by the coherent motion in the bulge, making it harder to derive accurate mass estimates. More than anything, the fast bulge rotation of NGC 7331 forces astronomers to rethink the blueprint of spiral galaxies. If other galaxies have similarly hidden dynamics at their cores, masked by orientation, dust, or limited resolution, it could mean our broader understanding of spiral formation and structure is incomplete. NGC 7331 becomes a testing ground, a laboratory for probing what happens when the heart of a galaxy beats faster than expected. And from a philosophical standpoint, this anomaly serves as a cosmic reminder. Even in systems that appear orderly and well understood, galaxies that resemble our own, there are still surprises lurking at the core. NGC 7331 teaches us that assumptions are only as good as the questions we're willing to ask. It's not enough to see a bulge and assume it behaves like every other. We have to dig deeper, measure more precisely, and open ourselves to the possibility that the universe has more variations than we've imagined. This fast-rotating bulge is more than an oddity. It is a window into a galactic mystery, a trait that elevates NGC 7331 from a typical spiral into a cosmic enigma. As we continue to observe it with higher resolution instruments and more sensitive spectrographs, we may inch closer to understanding the processes that drive this unexpected motion. Until then, the core of NGC 7331 spins on, quietly, powerfully, and just beyond the edge of full comprehension. Deep within the radiant heart of NGC 7331, behind the fast-spinning bulge and the clouds of interstellar dust, lies a secret hidden in gravitational silence, the likely presence of a supermassive black hole, an object so dense, so powerful, and so fundamentally strange that it warps space and time around it. Though it emits no light of its own, its influence can be detected in the motion of stars and gas spiraling near the galaxy's center. This invisible engine may be the key to explaining not only the peculiar rotational behavior of NGC 7331's bulge, but also the dynamic environment that pulses throughout the galaxy's core. The idea that a supermassive black hole resides at the center of NGC 7331 is not based on visual observation. No telescope can image it directly, but rather on the subtle clues encoded in the motion of stars and the emission patterns of gas. These clues emerge when astronomers turn powerful spectrographs toward the galactic nucleus and measure the Doppler shifts of starlight. The speeds at which stars are moving, especially in the inner few hundred light-years, are astonishing. Their rapid orbits suggest the presence of an enormous unseen mass compacted into a space far too small to be explained by visible matter alone. Such a gravitational anomaly is the hallmark of a black hole, and in the case of NGC 7331, the data point towards something truly vast. Based on current velocity dispersion models and comparisons to similar galaxies, the estimated mass of this central black hole may be in the range of several 100 million solar masses. That's hundreds of millions of times the mass of our Sun, all compressed into a singularity occupying a space smaller than our solar system. It's a cosmic monster, quietly lurking beneath the glow of the central bulge. This isn't unique to NGC 7331. Most large galaxies are believed to host supermassive black holes at their centers. What makes this one particularly intriguing is how its presence seems to correlate with the extraordinary dynamics of the bulge. While in many galaxies the central black hole plays a more passive role, in NGC 7331, it might be actively shaping the motion of stars across a broader region than usual. The high rotation speed of the bulge, unusual for its type, could be influenced by the gravitational pull of the black hole, especially if the black hole formed early and grew rapidly, setting the stage for the dynamic equilibrium that now exists. This leads to several important questions. Did the black hole cause the bulge to spin faster, or did it simply grow within a rapidly rotating bulge that was already in motion? Could there have been a period in the galaxy's past when the black hole was active, accreting matter at high rates and lighting up as a quasar or active galactic nucleus, AGN? While NGC 7331 shows no signs of current AGN activity, there's no bright X-ray core or radio jet blasting from its center. The past is not so easily read. Some astronomers speculate that the galaxy may have gone through such an active phase long ago, only to quiet down as its fuel supply diminished or stabilized. Even in its dormant state, the black hole exerts immense influence. Stars that wander too close are accelerated to dizzying speeds or torn apart entirely. Gas clouds that drift inward may spiral into the event horizon, heating up to millions of degrees and emitting X-rays and ultraviolet radiation just before they vanish forever. While these emissions are not currently prominent in NGC 7331, sensitive surveys have detected subtle infrared and X-ray signals near its core, hints of low-level accretion activity, suggesting the black hole is not entirely asleep. Moreover, the existence of this central black hole provides astronomers with a critical piece of the puzzle in understanding galaxy black hole coevolution. Over the past few decades, studies have revealed a strong correlation between the mass of a galaxy's central bulge and the mass of its black hole. This implies a deep and possibly causal connection between the formation of stars and the growth of black holes. NGC 7331 adds nuance to this story. Its fast-rotating bulge and likely massive black hole raise the possibility that there are different pathways to this coevolution, ones that don't necessarily require violent mergers or bar-driven gas inflows, but instead rely on more subtle, internal dynamics. In this way, NGC 7331 becomes more than a data point. It becomes a case study in how galaxies grow from the inside out, how a single gravitational anomaly can sculpt the rotation, structure, and evolution of an entire system. The presence of a supermassive black hole isn't just a curiosity. It's a foundational element of the galaxy's identity. And it may even help explain why this galaxy, so similar to the Milky Way on the surface, behaves so differently beneath. In many ways, NGC 7331 represents an ideal testbed for studying the effects of dormant black holes. It's close enough, just 40 million light-years away, for detailed observations, but far enough to give us an external view of the core. It's active enough to produce measurable rotation curves and gas dynamics, but quiet enough to offer a steady, unblinding view of the core. And it's mysterious enough to keep astronomers returning to its central region, searching for evidence, modeling its gravitational profile, and trying to piece together the story of a bulge that spins too fast, beneath which an invisible colossus may lie. Future observations with next-generation telescopes, like the James Webb Space Telescope and future extremely large ground-based observatories, may yet reveal more. By peering into the mid-infrared and radio regimes, astronomers might uncover evidence of past AGN activity, or detect signs of a slowly feeding black hole at the heart of this galaxy. Precision velocity mapping could refine mass estimates and determine the true extent of the black hole's sphere of influence. And over time, as our ability to model galactic dynamics improves, NGC 7331's core may give up more of its secrets. But for now, the mystery remains. A galaxy shaped by swirling arms and glowing stars, but anchored by a darkness that cannot be seen. A central engine that turns no wheels but bends every orbit around it. A bulge that breaks expectations, and a black hole that may be the reason why. In most spiral galaxies, the bulge behaves like an ancient citadel, massive, settled, and slow to stir. Composed largely of old stars, bulges usually rotate more sluggishly than the surrounding disk, their stars orbiting in varied, often random directions, held together by gravity more than momentum. But NGC 7331 defies this quiet archetype. Its central bulge, already prominent in size and brightness, doesn't just rotate. It outpaces the rotation of its outer disk. This anomaly has caught the attention of astronomers for decades because it flies in the face of how we typically understand galactic motion and structure. To fully appreciate how strange this is, it helps to understand galactic rotation norms. In a typical spiral galaxy like the Milky Way, the outer disk, the broad region where spiral arms lie, is where most of the dynamic rotational energy is found. Gas, dust, and stars in the disk orbit the galactic center at hundreds of kilometers per second, creating the familiar spiral shape due to density waves. The bulge, by contrast, is more spheroidal and tends to rotate more slowly. Its stars orbit in more elliptical, randomly inclined paths, leading to a pressure-supported structure that looks more like a miniature elliptical galaxy embedded at the core of a spiral one. But NGC 7331 throws this textbook example out the window. Observations of its central region, particularly from high-resolution spectroscopy, reveal that the inner bulge rotates faster than the surrounding disk material, a stunning reversal of what's expected. In numerical terms, While typical bulge stars and spiral galaxies may orbit at a few tens of kilometers per second, stars in NGC 7331's bulge have been clocked at velocities more than 300 kilometers per second near the core, surpassing even the outer disk's rotational speeds. It's a dynamical peculiarity that demands explanation. One reason this is so intriguing is that it challenges the standard formation scenarios for bulges. A classical bulge forms rapidly in the early universe, often through violent processes like galaxy mergers. These events scatter stars in all directions, resulting in a bulge that's dynamically hot, meaning that stellar motions are random and not rotationally aligned. But NGC 7331's bulge appears dynamically cold. Its stars share a common direction and speed, moving in a way more reminiscent of a spinning disk than a chaotic core. This has led some astronomers to propose that NGC 7331's bulge might not be a purely classical one. Instead, it could be a composite structure, combining a classical bulge with a rotationally supported pseudobulge formed through secular processes. Secular evolution refers to the slow, internal reshaping of a galaxy over billions of years, often driven by the redistribution of gas and stars by spiral arms or subtle gravitational instabilities. In this process, material from the disk gradually migrates inward, adding angular momentum to the core. Over time, this can build up a rotating component within the bulge, even if the original bulge was static or pressure-supported. The existence of such a fast-rotating bulge also raises questions about the role of past mergers or accretion events. While NGC 7331 appears relatively undisturbed today, its spiral arms are smooth and symmetric. There may have been a time in its history when it interacted with smaller galaxies. If those companion galaxies were gas-rich and merged with NGC 7331 in just the right orientation, they could have deposited angular momentum into the core, spinning it up while leaving the outer disk largely intact. This would be a subtle merger, not one of the violent collisions that completely scramble galactic structure, but a more delicate cosmic handshake that gradually tilted the dynamics of the core. Another factor may lie in the mass distribution of the bulge itself. NGC 7331's bulge is particularly luminous and dense. Its gravitational pull may be strong enough to hold together a faster rotating stellar population without flying apart. In this way, its very massiveness becomes a stabilizing factor, allowing it to rotate quickly while maintaining structural integrity. That rotation could be a stable equilibrium, rather than a transient phenomenon. And then there's the influence of the central supermassive black hole. While the black hole's gravity is strongest in the very innermost region, its presence could indirectly contribute to the dynamics of the bulge by influencing the orbits of stars over time. A fast-rotating bulge may also be more efficient at funneling material toward the black hole, leading to brief periods of activity and energy feedback. Over long timescales, this feedback could shape the density and angular momentum of the bulge in complex, still not fully understood ways. To make sense of all this, astronomers have turned to galactic simulation models, building virtual versions of NGC 7331 with varying initial conditions. By tweaking the gas content, merger history, and angular momentum distribution, they try to recreate a bulge that spins faster than its disk. In some cases, such outcomes are achievable, particularly when a significant portion of the bulge's mass comes from material originally part of the disk. These simulations point toward a scenario where NGC 7331 evolved through both calm and chaos, collecting the angular momentum of disk stars while preserving a layered, ordered structure. Even more curious is how rare this phenomenon appears to be. While fast-rotating bulges aren't entirely unheard of, they are not common. Among nearby spiral galaxies, most have bulges that rotate slowly, if at all. NGC 7331 stands out as one of the few systems where the central rotation is this pronounced. Its unique status makes it a prime candidate for long-term study, not just to understand this galaxy, but to test the limits of galactic formation theory more broadly. One emerging hypothesis is that galaxies like NGC 7331 represent a missing link, a transitional form between traditional spirals with classical bulges and the more disk-dominated, high angular momentum galaxies we observe in more isolated regions of the universe. They show us what happens when internal processes, rather than external forces, shape a galaxy's heart. They demonstrate how rotation and symmetry can coexist, even in structures previously thought to be chaotic or static. For observers and theorists alike, NGC 7331 is a galaxy that resists easy categorization. It wears the outward trappings of a normal spiral, graceful arms, a dense bulge, a flat disk, but its inner workings tell a different story. Its bulge spins not because of some temporary disturbance, but as a long-standing feature of its structure. It is a reminder that galaxies, like people, often carry within them histories that are far more complex than appearances suggest. And perhaps that's the real lesson of NGC 7331's central bulge, that even in the most familiar structures, the cosmos holds room for surprise. A bulge that outpaces its own spiral arms. A core that refuses to sit still. A heart that spins faster than the galaxy around it. The curious case of NGC 7331's fast-spinning bulge isn't just an anomaly, it's a clue. In astronomy, when something defies the norm, it doesn't just pose a question, it points toward a deeper narrative, a buried history waiting to be uncovered. The fact that the central bulge of NGC 7331 rotates more rapidly than its disk is not simply a mechanical oddity. It may be the fingerprint of ancient cosmic events, etched into the very heart of the galaxy. And it pushes astronomers to rethink what we thought we knew about how spiral galaxies form, evolve, and carry the legacy of their pasts. One of the most compelling avenues of investigation lies in galactic merger history. Though NGC 7331 looks serene today, its spiral arms graceful, its structure intact, it may have once endured periods of profound disruption. Unlike the dramatic major mergers that lead to elliptical galaxies, minor mergers, involving small satellite galaxies absorbed by a much larger one, can inject just enough energy and angular momentum into the system to reshape it from within, without tearing it apart. Imagine a small, gas-rich galaxy spiraling into NGC 7331 on a path aligned with its rotation. As the smaller galaxy is consumed, its stars and gas are incorporated into the larger system. If the merger happens with just the right trajectory and velocity, it can transfer angular momentum directly into the bulge, effectively spinning it up. Over time, the turbulent aftermath would settle, the stars would redistribute, and the spiral structure could reassert itself. But the bulge would remain altered, a relic of the encounter, spinning faster than before, preserving a fossilized record of a collision long past. Evidence supporting this scenario comes from stellar population studies. If we examine the light from the bulge and disentangle it into its component spectra, we can infer the ages and metallicities of the stars. A bulge that formed purely in the early universe, from rapid collapse and chaotic mergers, should be composed mostly of very old, metal-poor stars. But a bulge shaped partially by later interactions might show a more mixed population, older stars from the original structure blended with younger, more metal-rich stars formed from the inflowing gas of a satellite galaxy. Observations of NGC 7331 suggest that its bulge does indeed contain stars of varied ages, hinting that its formation was not a singular event but a layered process spanning billions of years. Another formation clue comes from secular evolution mechanisms, slow, internal processes that reshape galaxies from within, without requiring dramatic external interactions. In this context, NGC 7331's fast-rotating bulge could have gradually formed from the redistribution of gas and stars via spiral density waves or oval distortions in the disk. These features, which act like long-lived ripples, can channel gas toward the galaxy's center, where it cools, collapses, and forms stars. If enough material is transported inward over time, a new, more rotationally aligned structure can build up in the central region, a pseudobulge, spinning with the rhythm of the disk. In NGC 7331, the likely absence of a central bar complicates this explanation, since bars are typically the most efficient engines of secular evolution. However, recent studies suggest that non-barred galaxies are still capable of driving internal evolution, especially if they possess strong spiral arms or oval distortions in their inner disk. These features may be less visually obvious, but equally effective at redistributing mass. In this view, NGC 7331's fast-rotating bulge could be the product of an ancient disk instability, a gentle inward flow that lasted for eons and eventually built a rotating stellar core. There's also the possibility of a composite bulge, a structure formed by a combination of both violent and secular processes. In this scenario, NGC 7331 may have started with a classical bulge from early mergers, but over time, internal processes added a rotating component atop it. The result is a hybrid bulge, one that appears classical in shape and density but contains internal substructures that rotate more like a disk. Such bulges are rare but increasingly recognized as real features in spiral galaxies. They hint at a complex evolutionary past, a galaxy that didn't just grow from one mechanism, but from multiple phases of formation layered across time. Adding yet another layer to this mystery is the potential role of gas accretion from the intergalactic medium. Galaxies don't live in isolation. They're constantly drawing in diffuse gas from their surroundings, especially in more isolated environments where gravitational interactions are minimal. If NGC 7331 has been steadily accreting gas for billions of years, that gas could have migrated inward and settled into a fast-spinning inner disk, forming stars and slowly reshaping the bulge's kinematics from the inside out. This cosmic rain of material might explain not only the rotation but the layered age structure of the central region. Some models even suggest that in galaxies like NGC 7331, the bulge's rotation might be self-perpetuating. As more stars are born from inward-flowing gas, their angular momentum feeds the system, reinforcing the existing rotation. Over time, this can spin up the entire bulge to the point that it matches or even surpasses the disk's rotation. If true, this mechanism would mean that fast-rotating bulges aren't just remnants of a past event, they're evolving, living systems, constantly reshaped by internal feedback loops that regulate their own motion. Ultimately, the fast rotation of NGC 7331's bulge is more than an isolated trait, it is a diagnostic marker, a symptom of deep structural processes that have acted over billions of years. Whether it's spun up through minor mergers, internal inflows, gas accretion, or some combination of them all, its current state is the end product of countless small interactions and gradual transformations. The bulge is not a static lump of stars. It is a dynamic region shaped by the galaxy's entire life story, and in turn, it shapes the rest of the galaxy right back. Each of these formation clues pushes us to reconsider how spiral galaxies develop over time. They remind us that structure is not destiny, that the form a galaxy takes today is the product of a long, sometimes chaotic history written in motion, light, and silence. And NGC 7331, with its unusual bulge spinning faster than the arms that surround it, offers a rare glimpse into how complex, layered, and utterly unpredictable that history can be. Encircling the fast-spinning bulge of NGC 7331 is a grand and majestic disk, a luminous spiral of stars, dust, and gas that stretches out like a cosmic whirlpool into the quiet of space. It is in this disk where much of the galaxy's visible beauty resides, coiled in graceful arcs and streaked with the raw material of stellar creation. The spiral arms of NGC 7331 are not mere ornaments. They are dynamic highways of gravitational influence and molecular richness, teeming with activity and structure. And while the central bulge may be the galaxy's mystery, the disk and arms are its voice, speaking in light, shape, and motion. What immediately sets the disk of NGC 7331 apart is its striking definition. Even when viewed at its tilted orientation, the spiral structure reveals itself in remarkably clear patterns. The arms are long and well organized, sweeping outward in multiple arcs that wrap around the galaxy's core. Unlike many spirals whose arms appear disrupted, fragmented, or tightly wound, the arms of NGC 7331 give the impression of a coherent, well-formed structure, suggesting a stable and enduring gravitational rhythm that guides their formation. Within these arms lies a rich interstellar medium, composed of cold molecular clouds, atomic hydrogen, ionized gas, and dark dust lanes. This combination is essential for the process of star formation, and NGC 7331 appears to be particularly fertile. Observations across multiple wavelengths, optical, infrared, and radio, reveal that the galaxy is actively forming stars, especially in the spiral arms where gas is compressed by the density wave patterns that organize the disk. These are the galaxy's stellar nurseries, regions where gravity is slowly coaxing gas into stars, forging new light in the cold vastness of space. The presence of structured arms, meaning arms that show a clear and repeated spiral pattern rather than a chaotic scattering, also implies a mature density wave system. This concept, first proposed in the mid-20th century, suggests that spiral arms are not static structures made of fixed stars, but rather gravitational patterns through which stars and gas move. As gas flows through these arms, it is compressed, triggering star formation. The newly formed stars then illuminate the surrounding region, tracing the arm's shape in brilliant blue light. In NGC 7331, the contrast between the glowing arms and the dark dust lanes makes this process especially visible. In fact, these dark dust lanes, cool bands of interstellar matter that absorb and scatter light, run alongside the arms in a way that strongly resembles the Milky Way's own structure. But in NGC 7331, they may be even more pronounced. When viewed in silhouette against the galaxy's background stars, the dust appears to trace tight contours along the arms, suggesting that the arms are particularly rich in molecular gas. This dust is not evenly distributed, it clumps into clouds and filaments, marking the locations of future stars and perhaps even forming larger complexes that could give birth to stellar clusters or OB associations, groups of massive, hot, short-lived stars. The disk itself appears slightly thicker toward the center, where stellar populations begin to transition from the younger, bluer stars of the arms to the older, redder stars closer to the core. This gradient is typical in spirals, but in NGC 7331, the smoothness of the transition implies a quiet, ongoing process of stellar migration, where stars slowly drift inward over cosmic timescales, enriching the inner regions with time-aged populations. The outer disk, on the other hand, is studded with hot, young stars, evidence that the galaxy is still very much alive and active, creating new suns in abundance. Infrared observations, particularly from telescopes like Spitzer and the Herschel Space Observatory, have mapped the heat signatures of dust in the disk, showing that even regions obscured in visible light are bustling with energy. These wavelengths penetrate the dust and reveal glowing knots and filaments, signs of embedded star-forming regions not yet exposed in optical light. Meanwhile, radio telescopes detect the cold hydrogen gas, the raw material of star formation, and show that the disk is not only active today but likely has enough fuel to continue forming stars for billions of years to come. Interestingly, the symmetry and coherence of NGC 7331's arms may also reflect its relative isolation. In galaxies subjected to strong gravitational interactions, through mergers, tidal disruptions, or cluster dynamics, the arms can be pulled out of shape, broken, or even erased. But NGC 7331, residing in a quieter cosmic neighborhood, appears to have evolved without major disturbances, preserving the elegant spiral structure that we observe today. Its arms are not just features of beauty, they are testaments to stability, to a galaxy that has aged with grace, its rhythm uninterrupted by cosmic violence. This structure also provides astronomers with an opportunity to study the physics of spiral density waves and test models of star formation in well-defined galactic environments. By measuring the rate of star formation in the arms and comparing it with the density of gas and the speed of rotation, scientists can evaluate theories about how efficiently gas converts into stars under different conditions. NGC 7331 offers a real-world laboratory, with its structured arms and measurable parameters acting as a template for understanding broader spiral galaxy behavior. Additionally, the disk contains subtle features that hint at the galaxy's dynamic evolution. There are slight asymmetries, differences in brightness and structure from one side of the galaxy to the other, that suggest past perturbations. These could be the remnants of long-gone satellite galaxies, interactions that were minor enough not to destroy the spiral arms but still left a trace. In the outermost parts of the disk, some evidence suggests a slight warp, perhaps caused by the gravitational pull of unseen companions or dark matter substructure. These features remind us that even in galaxies that appear isolated, the dance of gravity never truly stops. In total, the disk and spiral arms of NGC 7331 present a picture of cosmic balance, between motion and stability, between structure and fluidity, between old stars and new beginnings. They are more than just luminous bands. They are engines of transformation, where gas becomes stars, where structure becomes story, and where the energy of rotation shapes the galaxy's very identity. While the fast-spinning bulge at the center draws attention for its defiance of norms, it is in the arms and disk where the ongoing life of NGC 7331 unfolds. It is here, in the structured spirals and star-forming clouds, that the galaxy tells us it is not merely a fossil from the early universe, but a living, breathing system, still changing, still building, still shining. Threaded across the brilliant arms of NGC 7331, like dark rivers winding through a glowing forest, are the dust lanes, dense, cold, and shadowy streaks that obscure starlight and draw sharp contrast against the surrounding brilliance. These are not mere aesthetic features. These dust lanes are the galactic wombs, where the raw ingredients of stars gather, collapse, and ignite. They are the veils of starbirth, concealing the most fundamental, dynamic processes of galactic evolution within their cold embrace. Dust in a galaxy like NGC 7331 consists primarily of tiny solid particles, microscopic grains of carbon, silicates, ices, and organic molecules, each smaller than the width of a human hair. Yet collectively, these particles absorb and scatter visible light, making the regions they inhabit appear darker when viewed in optical wavelengths. When astronomers peer into NGC 7331's disk using ground-based and space telescopes, these lanes show up as intricate silhouettes, jagged, snaking, and dividing the luminous spiral arms like celestial ink strokes across a glowing canvas. But within that darkness, hidden from ordinary sight, is where the real story unfolds. Inside these dust lanes lies molecular hydrogen, the most crucial element for star formation. However, molecular hydrogen is notoriously hard to detect directly. Instead, astronomers trace it through the presence of other molecules, like carbon monoxide (CO), which emits radiation in the millimeter and submillimeter wavelengths. Observations of NGC 7331 using radio telescopes like ALMA and other submillimeter observatories reveal rich clouds of CO gas spread throughout the dust lanes. These clouds are cold, often just a few tens of degrees above absolute zero, and massive, containing hundreds of thousands to millions of solar masses worth of material. They are known as giant molecular clouds, GMCs, and they are the nurseries of stars. Within these GMCs, gravity begins its quiet work. Slight instabilities, caused by pressure waves, galactic rotation, or even supernova shocks, cause regions within the cloud to collapse. As the gas compresses, it heats up and fragments, eventually forming dense cores. These cores are where protostars begin to form, initially hidden from view. Over time, as accretion continues and pressure and temperature rise, nuclear fusion ignites, and new stars are born. NGC 7331's dust lanes are full of these hidden birthing grounds. Infrared observations from telescopes like the Spitzer Space Telescope and the more recent James Webb Space Telescope have been pivotal in uncovering this concealed activity. While visible light cannot penetrate the dust, infrared light can slip through, allowing astronomers to peer into these cold regions and observe the telltale glow of young stellar objects, WISOs, infant stars still wrapped in the remnants of their birth clouds. These WISOs often cluster in tight knots along the dust lanes, glowing red and orange in the mid-infrared, surrounded by wisps of heated dust. And yet, the dust lanes of NGC 7331 are not uniformly productive. Some regions show higher star formation activity than others, and this variability reflects the complex interplay between gas density, turbulence, magnetic fields, and galactic rotation. In some arms, the dust appears thicker and more twisted, suggesting more turbulent conditions. In others, it aligns more smoothly with the spiral arm structure, creating ideal conditions for gravitational collapse and sustained star formation. This relationship between dust lanes and star birth is not unique to NGC 7331, but its clarity and richness make it an exemplary case. In fact, the structured, coherent nature of the spiral arms and dust lanes in this galaxy allows astronomers to map the progression of star formation across space and time. Often, newly formed stars can be seen just downstream from the dust lanes in the direction of rotation. This spatial offset is critical. It means that stars are forming inside the dense lanes, and then emerging from the clouds as they age and move along their orbits, lighting up the surrounding regions. The contrast is especially striking when comparing optical images with infrared ones. In visible light, the dust lanes appear as dark streaks cutting through the blue starlight of the spiral arms. But in the infrared, those same lanes glow with heat, revealing embedded star clusters, glowing polycyclic aromatic hydrocarbons, PHs, and the faint red halo of newly formed stars. These dual views give a more complete picture, one of ongoing birth, where darkness in one spectrum hides brilliance in another. There's also evidence that some of NGC 7331's dust lanes are shepherded by spiral density waves, long-lived gravitational patterns that help organize the gas into predictable paths. These waves don't move through the galaxy like a physical object. Instead, they're like stationary traffic jams, compressing gas as it flows through, triggering star formation as it enters, and leaving newborn stars behind as it exits. The dust lanes, therefore, are not just random accumulations of material. They are structural features shaped by the galaxy's gravitational choreography, repeating patterns that stretch across tens of thousands of light years. Occasionally, more dramatic events occur. Some parts of NGC 7331's dust lanes show signs of localized bursts of star formation, where clusters of massive stars form nearly simultaneously. These regions often appear in ultraviolet and H-alpha imaging as bright knots, the aftermath of a rapid stellar birth. The massive stars formed here live fast and die young, sometimes ending their lives as supernovae, which in turn inject energy into the surrounding interstellar medium, potentially triggering new waves of star formation or dispersing the remaining gas. This cyclical process, birth, death, and rebirth, is one of the most important engines of galactic evolution, and it plays out continuously within the dusty spirals of NGC 7331. And yet, dust lanes are not only sites of creation, they are also barriers and filters, shaping how we observe and interpret the galaxy. Their presence can block light from stars behind them, skew the apparent color and brightness of stellar populations, and complicate measurements of galactic mass and composition. This makes multi-wavelength observation essential. Only by combining visible, infrared, ultraviolet, and radio data can astronomers fully trace the interplay between dust, gas, and star formation across the galaxy. The dust lanes of NGC 7331 are more than obscuring features. They are the scaffolding of the future, the dark veins that pulse with the potential for light. They are the hidden half of the galaxy's story, quietly shaping its evolution from within. And they remind us that creation doesn't always blaze, it often begins in silence, in shadow, in the cold embrace of interstellar dust, where the next generation of stars awaits its moment to shine. NGC 7331, like any mature spiral galaxy, is a tapestry woven over billions of years, its structure defined not just by motion and gravity, but by the diverse populations of stars it contains. These stars are more than pinpoints of light. They are timestamps of the galaxy's long and layered history. And when we examine the stellar composition of NGC 7331, we find a vivid portrait of evolution, a galaxy alive with youthful brilliance in its spiral arms and seasoned with ancient starlight in its core and outskirts. The spiral arms are the most immediately vibrant regions of the galaxy. Here, we find abundant populations of young, hot, blue stars, the fresh results of ongoing star formation within the dense molecular clouds of the disk. These stars are typically massive, short-lived, and radiate brightly in ultraviolet and visible blue light. Their presence is a signal that NGC 7331 is not a passive relic of the past, but a galaxy in active growth, continuing to forge stars from the rich reserves of gas in its arms. These blue stars often appear in clusters or associations, sometimes numbering in the hundreds or thousands, depending on the size of the original cloud. The most massive among them, O and B-type stars, burn their fuel quickly and may only last a few million years before exploding as supernovae. In that brief window of existence, they exert a powerful influence on their surroundings, emitting strong stellar winds and ionizing radiation that shape the nearby gas and potentially trigger further waves of star formation. Interspersed with these young stars are intermediate-age stars, such as those in the F and G spectral types, many of which are forming from slightly older clouds or drifting into the arms from nearby regions. These stars form the structural backbone of the disk, populating not only the arms but the inter-arm spaces as well. They represent a bridge between the galaxy's current activity and its more ancient history, glowing less intensely than the young blue stars, but living far longer. Moving inward toward the galactic center, the stellar population shifts dramatically. The central bulge and inner halo of NGC 7331 are dominated by older, redder stars, the remnants of star formation that occurred in the galaxy's youth, billions of years ago. These stars are cooler, lower in mass, and have aged into the redder part of the spectrum. Their colors often span from orange to deep red, indicating a population of K and M-type stars, including red giants and subgiants that have long since left the main sequence. This age gradient, from young blue stars in the arms to old red stars in the bulge, is not just a visual curiosity. It tells us how the galaxy has evolved over time. The bulge likely formed early in the galaxy's history, either through a monolithic collapse of gas in the early universe or through the mergers and interactions that occurred during the galaxy's more chaotic youth. The stars formed during that epoch were born in a denser, more turbulent environment, leading to a population that is both older and more metal-rich than the primordial stars of smaller galaxies or globular clusters. And beyond the visible disk and bulge lies the halo, a sparse and faint region populated with some of the oldest stars in the galaxy. These halo stars often reside in globular clusters, tightly bound collections of tens of thousands to millions of stars that formed together in the distant past. The halo also contains stellar streams, remnants of smaller galaxies or clusters that were absorbed by NGC 7331 over billions of years. These streams and clusters trace the gravitational memory of long-vanished companions, revealing the cannibalistic side of galactic growth. The metallicity of the stars, meaning the abundance of elements heavier than helium, also varies across the galaxy and helps tell this story. Young stars in the arms tend to be more metal-rich, as they form from gas that has been enriched by countless generations of stellar evolution. The older stars in the bulge and halo often contain fewer heavy elements, reflecting the more pristine conditions of the early universe. This distribution aligns well with what we see in our own Milky Way, but NGC 7331's composition may be even more nuanced, as its bulge exhibits both classical and possibly pseudo-bulge features, suggesting multiple formation channels with slightly different stellar chemistries. Multi-wavelength studies, particularly those in optical and near-infrared, allow astronomers to create detailed maps of these stellar populations. By measuring the color and brightness of stars across different regions, scientists can reconstruct age gradients, trace stellar evolution, and even estimate the star formation history of the galaxy. For NGC 7331, these studies confirm a pattern of inside-out growth, where the oldest populations lie in the center and younger generations continue to form outward along the spiral arms. In recent years, integral field spectroscopy, using instruments like the MUSE spectrograph on the Very Large Telescope, has opened new doors for studying galaxies like NGC 7331. These tools allow astronomers to collect spectra across thousands of tiny regions within the galaxy simultaneously. With this data, scientists can analyze not just the overall composition, but how the kinematics and chemical makeup of stars change with position. In NGC 7331, such studies have hinted at complex motion patterns and metallicity gradients, offering further evidence of a long, layered history shaped by both internal evolution and external interactions. Altogether, the composition of NGC 7331 reveals a galaxy that is layered in time. Its arms glitter with youthful energy and creation, its center glows with the aged light of stars born billions of years ago, and its halo whispers of a past filled with collisions, accretions, and quiet endurance. The stars are its record keepers, each one a clock ticking through the epochs of galactic transformation. And perhaps most strikingly, when we examine this structure from afar, we see not just the story of NGC 7331, but a reflection of our own. The Milky Way, too, holds young stars in its arms, old giants in its core, and ancient clusters in its halo. In studying the stellar composition of NGC 7331, we're not just decoding the history of a distant spiral. We are glimpsing the broader blueprint of how galaxies like ours live, change, and carry their pasts within them. NGC 7331 sits proudly in the sky, appearing at first glance to be the dominant member of a small galactic entourage, a striking central figure surrounded by fainter, smaller companions. These nearby galaxies, labeled NGC 7335, NGC 7336, NGC 7337, and NGC 7340, seem to hover just beyond the spiral arms of their larger neighbor, as though orbiting around it in quiet deference. To the naked eye or even through modest telescopes, this alignment gives the impression of a compact galactic group, a miniature cluster anchored by the mass and majesty of NGC 7331. But this is a cosmic illusion. Despite their apparent closeness in the night sky, detailed observations reveal that these galaxies are not gravitationally bound to NGC 7331. Their association is a trick of perspective, a two-dimensional alignment projected onto the celestial sphere that masks the true three-dimensional distances separating them. While they lie in the same line of sight from Earth's vantage point, most of these smaller galaxies are much farther away, receding into the depths of space at significantly higher redshifts than NGC 7331 itself. Take NGC 7335 and NGC 7337, for instance. Both are small, elliptical or lenticular galaxies that lie in the immediate vicinity of NGC 7331 and sky coordinates. They can be seen in long-exposure astrophotographs as faint smudges set against the luminous spiral. However, redshift measurements, used to determine how fast these galaxies are moving away from us due to the expansion of the universe, show that they are receding at velocities far greater than NGC's 7331 zone. This means that, although they appear close on the celestial plane, they are actually located tens or even hundreds of millions of light-years farther away. The same is true for NGC 7336 and NGC 7340. While their placement near NGC 7331 gives the impression of proximity, spectroscopic data makes clear that they belong to entirely different regions of the universe. This misalignment of visual closeness and actual spatial distance is a common occurrence in deep space astronomy, where galaxies are scattered across billions of light-years but often appear to overlap or cluster in the limited dimensions of a two-dimensional sky map. This visual configuration has nonetheless led to these galaxies collectively being referred to as a group, often called the NGC 7331 group or more whimsically, the deerlick group, a name popularized by amateur astronomers due to the location's resemblance to an old observing site in upstate New York. The name stuck, and today, it's not unusual to see references to this group in astronomy literature, even though the gravitational reality tells a different story. From a scientific standpoint, this lack of physical association is quite significant. Real galactic groups, like our local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, are bound together by their mutual gravity. These groups often show signs of interaction and influence. Tidal tails from past collisions, bridges of hydrogen gas linking galaxies, or orbital patterns that betray gravitational tugs. In contrast, the galaxies near NGC 7331 show none of these interaction signatures. There are no bridges of material connecting them, no disrupted structures, and no shared motion through space that would indicate mutual gravitational pull. Instead, each galaxy is moving independently, shaped by its own history and cosmic environment. NGC 7331 itself is in a relatively isolated part of the universe, not situated in a dense cluster or tightly knit group. This isolation may partly explain its elegant spiral structure and lack of warping or obvious tidal distortion, features that are often altered by strong gravitational interactions in denser environments. That said, NGC 7331 is not entirely alone. While the so-called deerlick group may be a visual alignment, the surrounding region of space contains other galaxies, faint and distant, that offer context to its place in the larger cosmic web. These galaxies are not physically close enough to interact directly, but they trace the filamentary structures of dark matter and gas that organize the universe on its largest scales. In this way, NGC 7331 still participates in the broader architecture of the cosmos, one node in a vast network of galaxies and matter stretching across unimaginable distances. The illusion of the deerlick group also underscores one of the fundamental challenges in observational astronomy: the deceptive nature of two-dimensional projections. What we see through telescopes is often a flat rendering of a staggeringly deep three-dimensional structure. It takes precise measurement, spectroscopy, and redshift analysis to tease apart what is near from what is merely aligned. NGC 7331's story, therefore, is a reminder that appearances in astronomy are rarely the full truth, and that only through deeper investigation can we peel back the layers of cosmic perspective. Still, for astronomers and observers alike, the sight of NGC 7331 framed by its distant companions is a compelling one. It offers a beautifully composed scene, a grand spiral galaxy in the foreground, flanked by the dim ghosts of faraway ellipticals, each shining with its own ancient light. It is a visual poetry, even if not a physical cluster. And while they may not be gravitationally linked, these galaxies remain connected, not by force, but by the shared backdrop of the universe, and by the role they play in our understanding of galactic structure, illusion, and evolution. The grouping of NGC 7331 and its apparent companions has long captivated both amateur astronomers and professional observers, not just for its visual charm but for the peculiar story it tells, a tale of illusion, perception, and cosmic scale. Among telescope enthusiasts, this alignment has earned the nickname, the deerlick group, a name steeped in observation history and an almost poetic sensibility that contrasts sharply with the cold mechanics of astrophysics. The origin of the term, deerlick, is credited to the Deerlick Observatory, a private telescope site in the mountains of California, or alternatively to an old amateur observing spot in upstate New York. In either case, the term was adopted by the astronomical community as a more personal and evocative label for the set of galaxies that appears to huddle around NGC 7331 in the Pegasus constellation. The name stuck not because of scientific rigor, but because it captured the aesthetic unity of the scene, a grand spiral flanked by smaller companions, like a stag accompanied by its herd. From a purely visual standpoint, the deerlick group is stunning. In long-exposure astrophotography, NGC 7331 glows with its distinctive spiral arms and dust lanes, and nearby in the same frame, several faint galaxies, NGC 7335, 7336, 7337, and 7340, float like ethereal satellites. To the unaided eye or through a modest telescope, these galaxies appear scattered gently around their luminous neighbor, hinting at the kind of gravitational gathering we see in actual galactic clusters or compact groups. It is no wonder that amateur astronomers coined a term for it. The image feels cohesive, orderly, almost intimate. But as we now know, this arrangement is an optical coincidence. The galaxies are aligned along our line of sight but exist at vastly different distances from Earth. Their presence in the same visual field is a matter of celestial geometry, not gravitational physics. Nonetheless, this doesn't make the deerlick group any less compelling. On the contrary, it brings attention to the importance of observational context, how even seasoned astronomers must be cautious not to interpret sky maps at face value, and how beauty in the cosmos can often arise from chance alignments. Interestingly, this kind of misidentified grouping is not uncommon. Throughout the history of astronomy, many apparent clusters have turned out to be illusory. In earlier times, before the advent of spectroscopic redshift measurements, galaxies were often classified by appearance and proximity in the sky alone. It wasn't until the development of precise distance indicators, such as Cepheid variables, type Ia supernovae, and later, redshift velocity measurements, that astronomers could confidently distinguish between true gravitational associations and false projections. In the case of NGC 7331 and its visual neighbors, redshift data revealed the truth. While NGC 7331 lies around 40 million light-years away, most of the surrounding galaxies in the deerlick group are much farther, on the order of hundreds of millions of light-years distant. This revelation reframed the scene, shifting the deerlick group from a candidate compact cluster to a charming example of celestial serendipity. Still, this misnomer has not diminished its observational appeal. The deerlick group remains a popular target for backyard telescopes and astrophotographers, precisely because of its deceptive composition. There's a certain irony and elegance in capturing a cosmic vista where closeness is a trick of light, and yet the view is no less breathtaking. For many stargazers, the knowledge that these galaxies are not truly together enhances the sense of awe, an encounter with the depth and complexity of the universe, where what we see is just a projection on the vast canvas of space-time. Moreover, the term deerlick group highlights something profoundly human about astronomy, the desire to name, group, and connect what we see in the sky. Even as our tools grow more precise and our understanding more rigorous, we still look up and impose familiar metaphors on the unfamiliar. We still seek patterns, relationships, and narratives in the stars. This group, though not real in a gravitational sense, is very real in the cultural and emotional sense. It exists in the minds of countless observers who have aimed their telescopes at Pegasus and found themselves entranced by this celestial tableau. Even professional astronomers, aware of the group's false nature, continue to use the term in papers and catalogs, though typically with clarification, because it serves as a convenient label for a recognizable field. It's a reminder that astronomy is not just about equations and data. It's also about shared experiences, and the way we craft meaning from the night sky. In the case of the deerlick group, the meaning is layered. It's a case study in the limitations of visual observation. It's a demonstration of how redshift can dramatically change our understanding of spatial relationships. It's a snapshot of how cosmic scale defies intuition. And yet, it's also a simple, enduring example of how a small corner of the sky, just a tiny patch in the Pegasus constellation, can tell a story about depth, distance, illusion, and wonder. So while the galaxies in the deerlick group are not physically tethered, they are bound in another way, by our perspective, our tools, and our curiosity. NGC 7331, luminous and elegant, remains the star of the show. But its apparent companions, though far in the distance, play their part in the narrative, each shining across time and space to help us see the universe not just as it is, but as it appears. What makes the apparent companionship of NGC 7331 and its supposed group members so fascinating is the way it underscores one of astronomy's most persistent illusions, the cosmic trick of projected proximity. When we gaze into the sky, we're looking at a vast, three-dimensional universe flattened into two dimensions, where light from near and far objects converges on a single point in our line of sight. It's easy, almost instinctive, to assume that objects seen close together in the sky are also close together in space. But in the cosmos, distance is deceptive. The illusion of closeness in the deerlick group is a perfect example of this. On photographic plates and even through modest telescopes, galaxies like NGC 7335, 7336, 7337, and 7340 sit nestled around the luminous spiral of NGC 7331, as if orbiting companions in a coherent galactic family. Their arrangement feels purposeful, almost architectural, and the human brain, wired to seek patterns and relationships, can hardly resist the narrative, a dominant spiral galaxy with its elliptical companions in tow. But the universe isn't arranged for human perception. In reality, this grouping is a visual coincidence, a projection created by the alignment of vastly separated objects. These smaller galaxies, though appearing to huddle near NGC 7331, are in fact much farther away, often by tens or even hundreds of millions of light-years. They lie not in the same galactic neighborhood, but in entirely different cosmic districts, separated by unimaginable gulfs of time and space. The primary tool we use to unravel this illusion is redshift, the shift in spectral lines caused by the expansion of the universe. As galaxies move away from us, the light they emit stretches toward the red end of the spectrum. By measuring this redshift, astronomers can calculate a galaxy's recessional velocity and, by extension, estimate its distance from Earth. When this technique was applied to the so-called members of the deerlick group, it became immediately clear that only NGC 7331 resides at a distance of about 40 million light-years, while the others are much more remote, placing them far beyond any gravitational influence the primary galaxy could exert. This discovery reframes everything. What appears as a local cluster is in fact a cosmic lineup, a rare and visually striking alignment of galaxies at radically different depths along our line of sight. It's as though we're looking through a galactic keyhole, with foreground and background objects coinciding just so, forming a visual pattern that dissolves upon deeper analysis. This kind of illusion is not unique to the deerlick group. Astronomers have encountered similar cases throughout the sky. Stars, for example, often appear in constellations that seem to trace coherent patterns, like Orion's Belt or the Big Dipper, but are actually spread across vast distances. The stars merely align from our Earth-based perspective. Likewise, many galaxy clusters once thought to be physical groups turned out, under the scrutiny of redshift surveys and modern imaging, to be chance projections of unrelated galaxies. Such illusions can even occur at larger scales. What might appear to be a wall or filament of galaxies in a sky survey could, in fact, be a stacking effect, a layering of galaxies at multiple distances, all aligned within the narrow depth of a survey slice. Only with full spectroscopic data and 3D mapping can astronomers separate the cosmic wheat from the chaff, revealing which structures are gravitationally connected and which are illusions of angle and light. The implications of these illusions extend beyond astronomy's observational quirks. They highlight the limitations of human intuition when dealing with astronomical distances. On Earth, our senses are honed for nearby phenomena. We judge size, distance, and relationship based on visual cues, parallax, and occlusion. But those tools fail us when looking at the sky. The brain's urge to interpret a two-dimensional image as a three-dimensional space leads us to see false clusters, phantom companions, and illusory associations where none exist. And yet, there's a certain beauty in this deception. The illusion of proximity in the deerlick group gives us something rare, a compelling, photographic composition of galaxies at different depths, laid out in a way that's aesthetically pleasing and educationally rich. It allows us to explore the interplay between appearance and reality in the universe. It serves as a springboard for discussions about redshift, distance measurements, and cosmic scale. It challenges us to think critically about what we see and what we know. In educational settings, this illusion becomes a teaching tool. Students learning about galaxy classification and cosmic structure can see firsthand how appearances can mislead, and why observational astronomy requires more than just visual data. By analyzing redshift values and comparing them with apparent brightness and position, they begin to develop the scientific literacy necessary to understand the true architecture of the universe. Even seasoned astronomers are not immune to the power of such illusions. For every spectacular discovery grounded in hard data, there are thousands of images and alignments that tug at the imagination, that tease with the possibility of structure and relationship. That's why careful cataloging, precise measurement, and multi-wavelength analysis remain essential. In the end, the illusion of proximity is a reminder of the universe's complexity, and of the humility required to interpret it correctly. Yet perhaps there's also value in the illusion itself. The deerlick group, though not a real cluster, has captured the curiosity of countless observers. It has drawn attention to NGC 7331, invited deeper study, and inspired questions about the nature of galactic associations. It has served, paradoxically, as both a mistake and a map, a misreading that led to a more accurate understanding, a mirage that pointed the way to real truths. In the ever-deepening pursuit of cosmic knowledge, such illusions aren't detours, they're landmarks. They mark the places where our perceptions must be refined, where technology lifts the veil, and where curiosity evolves into comprehension. The galaxies that appear near NGC 7331 may not be close in space, but in the mind of the observer, in the data of the scientist, and in the poetic structure of the sky, they remain linked, an illusion, yes, but one that brings us closer to the truth. NGC 7331, unlike many of its spiral cousins nestled in crowded galaxy clusters or actively interacting groups, finds itself in a relatively quiet and isolated patch of the cosmos. This solitude, this lack of close, gravitationally bound neighbors, grants astronomers a rare and valuable opportunity: the ability to study the long-term evolution of a massive spiral galaxy with minimal interference from external forces. In the turbulent social life of the universe, NGC 7331 stands apart, more of a recluse than a mingler, and in its calm, we find clarity. This isolation is not absolute. As we've seen with the so-called deerlick group, NGC 7331 is not visually alone. The field around it is scattered with background galaxies, some quite distant, and it still participates in the large-scale structure of the universe. The filaments and sheets of the cosmic web that stretch across billions of light-years. But what it lacks is close, massive companions that are gravitationally entangled with it. No Andromeda-like neighbor, no tight cluster environment where galactic mergers and tidal interactions dominate the landscape. This is significant. Galaxies in dense environments are shaped dramatically by their surroundings. They are stretched by tidal forces, stripped of their gas by ram pressure interactions, and occasionally cannibalized or merged with their neighbors. While such processes are essential to our understanding of galaxy formation and transformation, they also make it hard to isolate internal evolutionary processes from the external chaos. It's like trying to study how a tree grows while it's being constantly battered by storms and invasive roots from surrounding flora. NGC 7331 offers the opposite, a chance to observe a massive spiral galaxy unfolding more or less according to its own internal physics, guided by the dynamics of its dark matter halo, the angular momentum of its primordial gas cloud, and the long rhythms of star formation cycles. Because of this, NGC 7331 serves as something of a laboratory for secular evolution, the slow, intrinsic changes in galactic structure and behavior that occur without major external disturbance. Astronomers use the term field galaxy to describe such objects, and NGC 7331 is a prime example. It is massive, luminous, and structurally complex, but it is not part of a larger gravitational assembly. This makes it an ideal benchmark for comparison. When studying galaxies in clusters, where environment plays a major role in shaping features like gas content, star formation rate, and morphology, researchers often compare them to field galaxies like NGC 7331 to determine what changes are intrinsic versus environmentally driven. For instance, NGC 7331's star-forming regions can be mapped and analyzed without the confounding variable of ram pressure stripping, a process where intergalactic gas in clusters rips away a galaxy's internal gas as it moves through the dense medium. Likewise, its dust lanes and molecular clouds have not been distorted by recent tidal interactions, which are common in clusters and groups. As a result, NGC 7331 retains a remarkably regular and symmetrical spiral structure, unmarred by the kind of warping or asymmetry that marks galaxies undergoing harassment or merger. Even its gas content, rich in hydrogen, with well-defined spiral arms of molecular material, points to an environment where gas accretion and consumption follow natural, uninterrupted cycles. In more crowded environments, gas can be stripped away or piled up in bursts due to external influence, skewing star formation rates. NGC 7331's relative isolation allows researchers to study how gas is converted into stars under steady-state conditions, providing insight into the natural life cycle of interstellar matter. Another benefit of this solitude is that it provides a stable platform for studying dark matter dynamics. In disturbed galaxies, mass distribution can be warped or asymmetric due to external tugs. But in a galaxy like NGC 7331, scientists can assume a more symmetric gravitational potential, making rotation curves and halo modeling more reliable. Indeed, Much of our understanding of spiral galaxy rotation and the inference of dark matter halos relies on systems like NGC 7331, massive, luminous, and structurally clean. The absence of large-scale interactions also makes NGC 7331 a perfect case for observing the long-term effects of internal feedback. Supernova explosions, stellar winds, and active galactic nucleus (AGN) activity can drive gas outflows, heat surrounding material, or suppress star formation. In a chaotic environment, it's difficult to attribute such changes to internal processes alone. But in a relatively undisturbed galaxy, we can trace the cause and effect of these feedback loops with greater confidence. Yet even in its isolation, NGC 7331 is not static. Galaxies are never truly frozen in time. Minor interactions, such as the accretion of small satellite galaxies or gas clouds, can still occur and leave subtle signatures. In fact, many isolated spirals, including NGC 7331, show signs of past accretion events, visible as stellar streams or faint halo distortions. These are remnants of long-ago encounters, absorbed gently rather than violently. Such minor mergers may even contribute to the peculiar rotation seen in NGC 7331's Bulge, as earlier discussed, by adding angular momentum or disrupting central dynamics in complex ways. In this sense, NGC 7331 serves not only as a template for isolated evolution, but also as a reminder that even isolation has a history. Galaxies like this carry scars of their past, quiet mergers, diffuse accretions, subtle gravitational interactions, that continue to influence their structure billions of years later. The difference is that in isolated systems, these influences are subtle, not overwhelming. They shape the galaxy rather than dominate it. Finally, the environmental context of NGC 7331 is crucial for understanding how galaxies like the Milky Way might evolve in the long term. Our own galaxy is not completely isolated. It shares space with Andromeda and dozens of smaller satellites, but it is also not in a dense cluster. In many ways, the Milky Way's environment is intermediate. Studying NGC 7331, therefore, offers a valuable window into one possible evolutionary pathway, a spiral galaxy growing and changing slowly, steadily, and largely on its own terms. Its solitude gives it strength, not in gravitational might, but in scientific value. In a universe often defined by chaos and collision, NGC 7331 is a rare example of cosmic composure, a stellar city that has thrived without neighbors jostling its borders. And in that quietude, it offers one of the clearest views yet into the undisturbed narrative of galactic life. Though NGC 7331 reveals much through optical observations, its brilliant spiral arms, dust lanes, and glowing core, some of its most vital secrets lie hidden from visible light. To truly understand what's happening inside this galaxy, especially in terms of how it grows, evolves, and gives birth to new stars, astronomers turn to the invisible ends of the electromagnetic spectrum, infrared and radio waves. These longer wavelengths penetrate dust, trace cooler temperatures, and reveal the building blocks of star formation, the very lifeblood of galaxies like NGC 7331. Infrared astronomy plays a crucial role in this endeavor. In the optical range, much of the galaxy's light is obscured by thick clouds of interstellar dust, especially along the spiral arms where star formation is most active. These dense regions block starlight and absorb photons, making it impossible to see what lies within using only visible wavelengths. But dust itself emits thermal radiation at infrared wavelengths, allowing infrared telescopes to peer through the murk and illuminate what's otherwise hidden. When infrared telescopes such as the Spitzer Space Telescope, WISE, or more recently the James Webb Space Telescope, JWST, turn their gaze toward NGC 7331, they uncover a galaxy bustling with stellar birth. Infrared observations reveal infrared luminous regions, massive stellar nurseries, where clouds of gas are collapsing under gravity to form new stars. These regions glow in the mid and far infrared bands, giving astronomers a direct measure of the current star formation rate. In NGC 7331, these active regions are distributed prominently along the spiral arms, matching the locations of dense dust lanes visible in optical images. But it's not just the current star-forming regions that infrared light reveals. It also traces the heated dust and complex organic molecules, polycyclic aromatic hydrocarbons, PAHs, that are created or illuminated by young, hot stars. These PAHs emit distinct spectral signatures in the infrared, and their distribution in NGC 7331 helps astronomers map where new stars have recently ignited, enriching their surroundings and shaping the local interstellar environment. Infrared data further reveal that NGC 7331 has a substantial bulge component emitting in the near-infrared, where older, cooler stars dominate. This helps astronomers better isolate the light of older stellar populations and measure the structure and mass of the bulge with more precision than optical wavelengths allow. Combined, these observations provide a multi-generational view of the galaxy's evolution, from dusty star-forming regions to settled stellar populations that have burned for billions of years. But the picture remains incomplete without radio astronomy. If infrared shows where stars are being born, radio waves reveal the raw material from which they form, cold neutral hydrogen gas, HI, molecular gas, especially carbon monoxide, CO, as a proxy for H2, and other cool interstellar medium components that cannot be seen in infrared or optical light. Using radio telescopes like the Very Large Array, VLA, or single-dish observatories such as the Green Bank Telescope, astronomers map the distribution of HI gas across NGC 7331. This gas, often extending far beyond the visible disk of the galaxy, represents a reservoir of potential future star formation. Radio maps show that NGC 7331 is rich in hydrogen, with a disk that flares out beyond its spiral arms, suggesting it is not only currently forming stars but has enough fuel to continue for billions of years. Additionally, molecular gas, the more direct precursor to stars, is detected using millimeter-wave telescopes like ALMA, the Atacama Large Millimeter/Submillimeter Array, or IRAM. Observations of carbon monoxide lines trace the densest regions of the interstellar medium, where clouds collapse and ignite into stars. In NGC 7331, CO maps align closely with infrared bright regions, confirming that where molecular clouds gather, star formation follows. Another advantage of radio observations is that they help trace the kinematics of gas in the galaxy. By observing the Doppler shift of hydrogen or CO lines, astronomers can construct detailed rotation curves, study spiral density waves, and assess the mass distribution, including the influence of dark matter. In NGC 7331, these curves show that gas continues to orbit at high speeds far beyond the visible edges of the galaxy, implying the presence of a substantial dark matter halo enveloping it. Radio observations also reveal non-thermal emission, such as synchrotron radiation from cosmic rays spiraling in magnetic fields. This emission, often linked to supernova remnants and galactic magnetic structures, can highlight regions of recent stellar death, where massive stars have ended their lives in explosions, returning energy and enriched material to the interstellar medium. These feedback processes are critical to understanding how star formation is self-regulated within the galaxy. Moreover, advanced surveys in radio and submillimeter wavelengths have hinted at subtle asymmetries and warping in the outer hydrogen disk of NGC 7331, potential signs of past accretion events, minor interactions, or gas inflow from the intergalactic medium. These features, invisible in optical wavelengths, speak to the long-term evolutionary processes that operate quietly in isolated galaxies. Together, the infrared and radio observations of NGC 7331 give us a holistic view of a living galaxy, one that is not just glowing with stars, but actively creating them, nurturing them in dust-shrouded cradles, feeding their birth with cool hydrogen, and recycling their remnants back into the cosmic cycle. They show a galaxy that is not static, but dynamic and regenerative, evolving over time through internal processes rather than external collisions. In essence, these wavelengths allow us to go beyond the surface, beyond what we see in beautiful optical images, and tap into the invisible infrastructure of galactic life. They reveal the fuel, the factories, the feedback, and the faint signatures of the past written into the coldest and darkest corners of the galaxy. In NGC 7331, they show us a system that is not only a mirror of the Milky Way in form but also in function and vitality, living and breathing across the entire electromagnetic spectrum. When astronomers look to NGC 7331, they often see something eerily familiar, and yet profoundly different. At first glance, this galaxy appears to be a cosmic twin of our own Milky Way. It's a large spiral, similar in size and brightness. It has elegant arms, a central bulge, and a structure that could easily pass for the face of our own galactic home, if we could somehow step outside and view the Milky Way from afar. But the resemblance, though striking, is not perfect. Upon closer inspection, critical differences emerge. Differences that reveal how two galaxies can look similar, yet follow divergent evolutionary paths. One of the most fundamental structural differences lies in the presence of a galactic bar. The Milky Way, like about 2/3 of all known spiral galaxies, is a barred spiral. This means that its spiral arms do not emerge directly from a round central bulge but instead from the ends of an elongated bar, a thick, rotating stream of stars, dust, and gas that stretches across the galactic core. This bar is thought to play a key role in funneling gas toward the center of the galaxy, feeding star formation and possibly even activity in the supermassive black hole that lurks at its heart. NGC 7331, on the other hand, lacks this bar. It is an unbarred spiral galaxy, classified as SASB in the de Vaucouleurs system. Its spiral arms flow directly from a luminous, rounded central bulge. This difference in bar structure isn't merely cosmetic, it suggests differences in internal dynamics, angular momentum distribution, and star formation processes. Bars are believed to evolve over time as galaxies grow and shift, so the absence of a bar in NGC 7331 might indicate that it's either in an earlier evolutionary phase, or that its particular mass distribution and history simply prevented a bar from forming at all. Another major point of comparison lies in the bulge structure and rotation. Both the Milky Way and NGC 7331 possess central bulges, concentrations of older stars that occupy the galactic core, but the behavior of these bulges is strikingly different. The Milky Way's bulge rotates, but not unusually so. Its movement is relatively moderate and well understood within the context of our galaxy's dynamics. NGC 7331, however, defies expectations. Its central bulge rotates faster than the surrounding disk, which is almost unheard of in massive spiral galaxies. This unusual feature has puzzled astronomers for decades. It suggests a complex and possibly tumultuous past, one that might involve past accretion events, mergers, or highly efficient angular momentum transfer in the early stages of its formation. In the Milky Way, the bar itself likely redistributes angular momentum between stars, gas, and the dark matter halo, which could help explain why its bulge does not rotate as rapidly. But in NGC 7331's unbarred structure, the mechanics behind its fast-rotating bulge remain an open mystery. Environmental context also plays a pivotal role in contrasting these two giants. The Milky Way is not alone. It resides in the Local Group, a gravitationally bound collection of more than 50 galaxies, including the Andromeda Galaxy, M31, the Triangulum Galaxy, M33, and a host of smaller satellite galaxies like the Magellanic Clouds. These companions are more than just neighbors. They influence the Milky Way's structure and future. In fact, the Milky Way and Andromeda are on a collision course, expected to merge in about 4 to 5 billion years. NGC 7331, by contrast, is far more isolated. While it has what appears to be a surrounding group, the so-called deerlick group, we've already discussed how those nearby galaxies are not actually gravitationally bound to it. This solitude makes NGC 7331 a cleaner laboratory for studying intrinsic galactic evolution without the added complexity of close gravitational interactions. It is not subject to tidal stripping or warping from large nearby galaxies, and there's no sign of a recent major merger like the one anticipated for our local group. Then there's the matter of satellite galaxies. The Milky Way has numerous confirmed satellites, small galaxies that orbit it, some of which are gradually being consumed. These satellites are useful for studying dark matter, tidal interactions, and galactic growth through hierarchical merging. In the case of NGC 7331, no major bound satellite system has been confirmed. This raises questions. Has NGC 7331 already absorbed its satellites in the distant past, leaving only faint traces? Or has it always existed in a relatively low-density environment where fewer such galaxies formed nearby? In terms of star formation, both galaxies are active, but again, differences emerge. The Milky Way has a moderate star formation rate of about 1 to 2 solar masses per year, concentrated in the spiral arms and especially in the molecular clouds near the galactic center and mid-disk. NGC 7331, based on infrared and radio observations, appears to have a slightly higher star formation rate, particularly in its more prominent and tightly wound spiral arms. Its star-forming regions are large and luminous, suggesting a steady inflow of gas and an efficient conversion into stars. This leads to the topic of spiral structure itself. The Milky Way's spiral arms, while mapped through radio observations, are not as well resolved from our position within the disk. It's difficult to know exactly how many major arms there are, or how symmetric they are. In contrast, NGC 7331's orientation, tilted just enough for us to see into its structure, gives us a clear view of multi-armed spiral symmetry, revealing dust lanes and star-forming regions with remarkable clarity. Additionally, the dark matter profiles of both galaxies show key similarities. Both exhibit rotation curves that remain flat at large radii, suggesting the presence of extensive dark matter halos. In both galaxies, the visible mass, the stars, gas, and dust, is not sufficient to explain the orbital speeds of stars in the outer regions. This shared trait makes NGC 7331 especially useful as a Milky Way analog in the study of galactic mass distribution and dark matter modeling. And yet, NGC 7331 is more than just an analog, it is also a contrast. It is the control group, in the experiment, the twin that grew up alone while the Milky Way matured in a bustling family of galaxies. Together, these two systems show the diversity of paths a spiral galaxy can take. They illuminate how structure, environment, and history shape the complex dynamics we observe. In a universe filled with billions of galaxies, these two serve as reminders of how much can be learned by comparing what is alike and what is not. NGC 7331 reflects the Milky Way in form, but not in detail. And that difference is where the science lives, where astronomers dig deeper to understand why galaxies look the way they do, and how the subtle variables of their birth and surroundings guide their destinies across cosmic time. NGC 7331 has long held a special place in the hearts of astronomers not only because of its stunning structure but because it offers something uniquely precious in cosmic terms, a stand-in for our own galaxy. The Milky Way, as vast and complex as it is, poses a major challenge to those who study it. We live inside it. Just as you can't easily grasp the full size and shape of a forest while standing beneath its canopy, we can't step outside the Milky Way to see its entirety. That's why galaxies like NGC 7331 become so important. They are our mirrors in the cosmos, our benchmark galaxies, reference points that allow us to study what we cannot directly observe in our own celestial backyard. Because NGC 7331 shares many structural and dynamical similarities with the Milky Way, it is frequently used by astronomers as a model system. When we need to understand how spiral arms behave in a massive disk galaxy, or how a central bulge evolves over time, or how dark matter halos influence the rotation of a galaxy, NGC 7331 offers a nearly ideal laboratory. Its orientation, slightly tilted rather than edge-on or face-on, means we can view both the disk and central regions with impressive clarity, granting a kind of 3D glimpse into a galactic anatomy that we can only guess at in the Milky Way. In particular, astronomers often use NGC 7331 as a template for interpreting observations of the Milky Way that are ambiguous or incomplete. For example, determining the exact number and layout of the Milky Way's spiral arms is notoriously difficult due to dust and our embedded vantage point. By analyzing the arm symmetry, spacing, and star-forming activity in NGC 7331, scientists can create more accurate models of how a similar mass and size spiral galaxy might be structured, and by extension, what our galaxy likely looks like from the outside. It's not just the visible structure that makes NGC 7331 so valuable. The way gas moves through its disk, the behavior of its rotation curve, and the distribution of dark matter inferred from the motion of stars, all of these features echo the conditions we believe exist in the Milky Way. In studying NGC 7331's extended HI disk, for instance, astronomers learn about the outer dynamics of disk galaxies, helping to explain the observed flatness and galactic rotation curves that originally led to the dark matter hypothesis. Since our own galaxy's outskirts are harder to measure directly, having a well-behaved analog like NGC 7331 is essential for making sense of the data. Even the difference between their central bulges, specifically NGC 7331's faster-than-expected bulge rotation, becomes a feature of interest. It sets a contrasting case against which to test assumptions about how bulges form. Does the Milky Way's slower-rotating bulge imply a calmer history, or does it simply reflect the effects of the galactic bar? Is NGC 7331 a glimpse of a different evolutionary trajectory, or does it represent what the Milky Way once looked like, or might become? This benchmark function becomes even more powerful when applied across multiple wavelengths. In optical, infrared, and radio observations, NGC 7331 is extensively mapped and catalogued, giving us a full spectral profile of a massive spiral galaxy in motion. These data can then be used to simulate what the Milky Way would look like if observed from the outside in those same wavelengths. That's especially important for missions like the Sloan Digital Sky Survey (SPITZR) and WISE, which collect galactic data in large surveys but rely on well-understood individual galaxies like NGC 7331 to calibrate and verify their algorithms. Even in the realm of galactic feedback and star formation, NGC 7331 provides a benchmark for comparison. Its star formation rate, although slightly higher than the Milky Way's, falls within a similar range. This allows astronomers to model how stars, once born, influence the interstellar medium through supernovae and stellar winds. The way these processes unfold in NGC 7331, without the added turbulence of interactions with large neighbors, serves as a cleaner reference for how feedback mechanisms might be working in our own galaxy. And in the context of the cosmic distance ladder, NGC 7331 plays another important role. Its relatively nearby location, about 40 million light-years, and well-resolved structure make it a target for various standard candles and distance indicators, Cepheid variables, tip of the red giant branch measurements, and even supernovae. By establishing an accurate distance to NGC 7331, astronomers strengthen the accuracy of distance measurements across greater scales, which in turn calibrates measurements for the Milky Way's structure and position in the cosmic web. In short, NGC 7331 is not just another pretty spiral in the night sky. It is an essential tool, a galactic reference frame against which the Milky Way can be studied, modeled, and understood. It fills in the blind spots left by our embedded perspective, allowing us to simulate an outside view of our own galaxy and test hypotheses that would otherwise be out of reach. It teaches us about what spiral galaxies can become when left to evolve in relative peace, and it sharpens our understanding of what makes the Milky Way both ordinary and extraordinary. And perhaps most poetically, it offers us a kind of cosmic mirror. When we look at NGC 7331, we are seeing not only a distant world of stars and gas, we are catching a reflection of ourselves. In its graceful arms and glowing core, we glimpse what might be the face of our own galaxy, seen from the other side of the cosmos. One of the most frustrating and fascinating realities of astronomy is that while the Milky Way is one of the most studied galaxies in the universe, it is also one of the most challenging to fully observe. We live inside it, embedded deep within one of its spiral arms, some 27,000 light-years from its center, and because of this position, our view is obstructed and distorted. The stars, dust, and gas that compose the galactic disk stretch across our sky like a luminous fog, making it nearly impossible to gain a clear, external perspective. We can measure parts of it. We can model its shape. But we can never truly step outside and look back. This is why galaxies like NGC 7331 are so vital to our understanding. They serve as stand-ins, cosmic proxies, for what the Milky Way might look like from a distant vantage point. Imagine trying to describe the architecture of a cathedral while standing inside a darkened hallway of it. You might catch glimpses of vaulted ceilings and stained glass, but you can't see the spires, the flying buttresses, or the full symmetry of the structure. You'd need a drone, or in astronomical terms, a telescope focused on a similar cathedral from across the street. That's exactly what NGC 7331 offers. From our location within the Milky Way, many parts of the galaxy are not just hard to see, they are effectively invisible in optical light. Thick clouds of interstellar dust obscure our view along the galactic plane, especially toward the center where the Bulge and bar dominate the structure. Even with powerful telescopes, we must rely on radio and infrared observations to peer through these veils, and even then, the picture is fragmented. This means that large-scale features like the exact number of spiral arms, the true extent of the galactic disk, or the exact shape of the Milky Way's halo must be inferred, not directly seen. In contrast, NGC 7331 lies far beyond the interference of our local perspective, and it sits at an ideal angle, slightly inclined from our point of view. This orientation is perfect for study. It allows astronomers to observe both the face-on spiral structure and the vertical thickness of the disk, as well as the central bulge and outer halo, features that remain elusive when studying the Milky Way from the inside out. Because of this, it's not just a similar galaxy, it's a galaxy we can actually see in full. By studying how NGC 7331's spiral arms are laid out, how they connect to the bulge, how star-forming regions light up the dust lanes, and how the outer gas rotates in response to the galaxy's mass, we can build a more complete model of the Milky Way. If a certain pattern appears in NGC 7331, and we observe something similar in a patch of sky from within our own galaxy, we can make more confident assumptions about what's happening on a larger scale. It becomes a kind of cosmic Rosetta Stone, translating external structure into internal understanding. This extends even to fundamental measurements like the thickness of the galactic disk or the extent of the dark matter halo. While we have some information about the Milky Way's dimensions, estimates of a disk roughly 100,000 to 120,000 light-years across, with a thickness of about 1,000 light-years, those figures are averages based on scattered data points. By studying a galaxy like NGC 7331 with a clear, edge-to-face perspective, we can see how stars are distributed vertically, how gas behaves at the edges, and how rotation speeds vary with distance. These patterns then inform the numerical simulations we use to model the Milky Way's unseen structure. There's also the matter of galactic features that may be unique or uncommon. For example, the Milky Way has a central bar, while NGC 7331 does not. This difference allows astronomers to contrast how bars influence star formation, angular momentum, and bulge dynamics. If a phenomenon is present in the Milky Way but absent in NGC 7331, it offers a point of comparison that can help identify what is intrinsic to our galaxy and what is shared more universally. This proxy relationship is especially powerful when used across multiple wavelengths. In the radio, we observe how gas is distributed and how it moves. In the infrared, we see where stars are forming and how dust is heated. In the optical, we observe the distribution of stellar populations. By layering these datasets for NGC 7331 and comparing them to what we can detect from within our own galaxy, we form a multidimensional image of what the Milky Way would look like from a cosmic distance. Even the large-scale rotation of the galaxy, its rotation curve, is better understood through this comparative lens. We know that stars in the Milky Way rotate at roughly constant speeds even far from the galactic center, indicating the presence of dark matter. But because we can't watch this rotation from an external frame, we rely heavily on analogs like NGC 7331 to verify these behaviors. When we see that NGC 7331 exhibits the same flattening of its rotation curve, despite being seen from the outside, we gain confidence in our models of the Milky Way's invisible halo. In effect, studying NGC 7331 is like having access to a scale model of our galaxy, frozen in time and suspended in space where we can inspect it from all sides. It doesn't replicate every feature of the Milky Way, but it comes close enough, and its observable structure allows us to fill in the blanks that our internal perspective leaves empty. Without galaxies like NGC 7331, our understanding of the Milky Way would be limited to piecemeal reconstructions, like archaeologists trying to rebuild a temple from shards and ruins. With it, we gain the ability to see the temple standing, not just imagine it. And perhaps most significantly, it reminds us just how hard it is to study something from within. The human experience of being inside the Milky Way, gazing outward at the universe, is both a gift and a challenge. We are surrounded by stars, immersed in a cosmic disk of light, but that very immersion makes it impossible to grasp the full picture without help. Galaxies like NGC 7331 offer that help. They are our external mirrors, our distant reflections, showing us what we are too close to truly see. One of the most revealing and revolutionary tools in modern astrophysics is the galactic rotation curve, a plot that shows how fast stars and gas orbit around a galaxy at various distances from its center. These curves are more than just scientific graphs, they're cosmic fingerprints. They expose the unseen structures beneath the visible layers of a galaxy. And in the case of NGC 7331, its rotation curve not only follows some expected trends, but also presents surprising deviations, especially in its bulge, offering an even deeper mystery. To understand just how important these rotation curves are, consider what one might naively expect. In a solar system, planets farther from the Sun move more slowly because they're less tightly bound by gravity. If you applied that same logic to galaxies, assuming most of the mass is in the luminous matter like stars and gas, you would expect the orbital speed of stars to decrease with distance from the galactic center. But that's not what happens. In the 1970s, astronomers like Vera Rubin and Kent Ford discovered that in galaxies like NGC 7331, stars in the outer regions keep orbiting at roughly constant speeds, even far beyond where most of the visible matter lies. This flattening of the rotation curve was the first strong observational evidence for something massive and invisible: dark matter. If only visible matter were responsible for the galaxy's gravity, the outer stars should be flying off into intergalactic space or slowing down significantly. But they don't. Something else must be there, something with mass, yet invisible, providing the necessary gravitational pull. This unseen mass forms a dark matter halo surrounding the entire galaxy, extending far beyond its visible edge. NGC 7331 exhibits just such a rotation curve. Radio observations of neutral hydrogen gas, HI, far from the center show that the orbital velocity stays nearly flat, even as the density of stars drops off dramatically. This supports the now widely accepted idea that dark matter dominates the mass budget of large spiral galaxies. NGC 7331's data serve as a strong confirmation of this theory. Its rotation curve behaves similarly to that of the Milky Way, which is why it's so often used as a reference for dark matter studies. But NGC 7331 doesn't just offer validation, it adds new complexity. Its central bulge shows unusually fast rotation, something not typically seen in spiral galaxies. In most galaxies, including the Milky Way, the bulge is composed of older stars moving in more randomized orbits with only moderate net rotation. In NGC 7331, however, the bulge spins faster than the surrounding disk, flipping the usual expectation. This fast-rotating bulge has profound implications for our understanding of mass distribution and angular momentum in galaxies. It suggests that the bulge might not be a simple, spheroidal population of stars that formed early in a galaxy's life. Instead, it may be a pseudobulge, formed from disk material that was funneled inward and spun up, perhaps through internal processes like disk instabilities or even minor mergers. If so, this changes how we interpret the inner dynamics of NGC 7331 and others like it. This kind of detailed rotation data is essential for testing alternative theories of gravity as well. While most scientists agree on the existence of dark matter, some physicists have proposed modified gravity models to explain the flat rotation curves without invoking invisible mass. Galaxies like NGC 7331, with their unexpectedly complex internal motions, provide key observational constraints for these theories. If modified gravity can explain the fast bulge or the flat outer curve without dark matter, then the theory falls short. Conversely, if it can, we may have to rethink one of the foundational components of modern cosmology. The rotation curve of NGC 7331 also helps astronomers fine-tune simulations of galaxy formation. In computer models, researchers try to recreate galaxies from the Big Bang forward, using physics to guide how gas collapses, stars form, and structures evolve. These simulations must reproduce observed rotation curves to be considered accurate. When they don't match reality, when, for instance, they fail to predict the correct balance of bulge and disk rotation seen in NGC 7331, it tells us that something is missing in the model. Maybe the feedback from star formation is too weak. Maybe the interaction between dark matter and baryonic matter isn't being simulated correctly. Either way, galaxies like NGC 7331 refine our cosmological toolkit. On a more granular level, the galaxy's rotation curve gives insights into the local gravitational potential at various radii. This affects how stars move, how spiral arms form and propagate, and even how gas clouds collapse to form stars. For example, the location and shape of spiral arms are influenced by the orbital speeds of stars and gas. If the disk moves too quickly or too slowly at certain radii, the spiral pattern will change. The balance of shear and rotation directly affects galactic morphology, which is one reason NGC 7331 has such clean, symmetrical arms. Its dynamics are internally consistent. Furthermore, the speed at which stars orbit tells us something about the stability of the disk. In NGC 7331, the relatively smooth rotation curve, along with the fast-rotating bulge, may contribute to a more stable structure, allowing star formation to proceed in well-defined spiral patterns rather than chaotic bursts. This helps explain why NGC 7331 appears so organized and tranquil, especially when compared to galaxies that have recently undergone mergers or tidal disruptions. Interestingly, the outer reaches of NGC 7331's rotation curve also hint at asymmetries and possible warps, likely caused by interactions with the intergalactic medium or past minor accretion events. These subtle deviations provide a clue that even seemingly isolated galaxies have a dynamic history written into the motions of their stars and gas. NGC 7331's rotation curve is far more than a chart of speed. It's a record of the galaxy's past, a roadmap of its structure, and a cipher for decoding one of the greatest mysteries in the universe: the nature of dark matter. Its behavior confirms what we see in the Milky Way, but it also offers enough differences, like the fast bulge, to challenge our assumptions and push our understanding forward. Each measurement, each data point, deepens the story. From the spinning heart of the bulge to the whispering edge of its gas-rich outer halo, NGC 7331 moves not in silence, but in revelation. Its rotation speaks volumes, and we're still listening. The peculiar behavior of stars within NGC 7331's disk and bulge doesn't just add a layer of complexity to its structure, it provides critical evidence pointing toward one of the most elusive components of the universe: dark matter. While this mysterious substance cannot be seen directly, emitting no light or energy, it reveals itself through gravity, shaping the cosmos on every scale. And in NGC 7331, dark matter's presence is written into the very way the galaxy spins. Let's start with the basic observational fact. Stars in the outer regions of NGC 7331 are moving far faster than they should be if only the visible matter, the stars, gas, and dust, were creating the gravitational pull. In Newtonian physics, if mass were concentrated in the galaxy's luminous regions, then as you move outward from the center, the gravitational attraction would weaken, and so would orbital velocity. The rotation curve should slope downward, much like the outer planets in the solar system orbit the sun more slowly than the inner ones. But that's not what happens. In NGC 7331, And in galaxies like it, the rotation speed remains remarkably constant far into the galactic outskirts. This phenomenon creates what's called a flat rotation curve. The flatness of this curve is impossible to explain without invoking a hidden mass component, one that extends well beyond the visible edge of the galaxy. The stars are moving too fast to be held in place by the gravity of visible matter alone. Something unseen must be providing the extra mass needed to generate that much gravitational force. This invisible structure is what we call the dark matter halo, a vast, spherical distribution of dark matter enveloping the entire galaxy, possibly extending hundreds of thousands of light-years beyond the luminous disk. In NGC 7331, the case for a dark matter halo becomes even stronger when we examine the contrast in how stars move in different parts of the galaxy. The central bulge rotates faster than expected, defying the norms of galactic dynamics. Meanwhile, the outer disk maintains high rotational speeds where, again, there's too little visible matter to account for the motion. This disconnect between the inner and outer regions of the galaxy, two components that seemingly follow different rules, suggests that the dark matter halo doesn't just hover on the outskirts. It penetrates deep into the core, subtly shaping the internal dynamics of the bulge and the disk in different ways. But how do astronomers know this? How do they measure the influence of something they can't see? It begins with observational data collected across multiple wavelengths. Radio telescopes, for example, are crucial in mapping the distribution of neutral hydrogen gas, HI, in the outer disk. This gas extends much farther than the visible stars and provides a clean tracer for orbital velocities at great distances from the galactic center. By measuring the Doppler shift in the radio emissions of this gas, astronomers can determine how fast it's moving, and these measurements invariably show the same surprising result: the speeds don't drop off. Next come optical and infrared observations of the stars in the disk and bulge. Spectroscopy allows astronomers to track the velocity of stars by measuring the redshift and blue shift of their light as they orbit the galaxy's center. When these velocities are plotted as a function of distance from the center, the rotation curve is built, and in NGC 7331, it shows that same characteristic flatness in the outer disk, and unexpected speed in the bulge. Now, using this rotation curve, astronomers can calculate how much gravitational force is needed at each radius to keep stars in orbit. From this, they derive the total mass enclosed within each radius. Then they compare that to the visible mass, what we can account for through stars, gas, and dust. In the case of NGC 7331, the visible matter falls far short. The discrepancy becomes clear. The galaxy must contain much more mass than what we can observe directly. This excess mass, dark matter, forms the structural scaffold that holds the galaxy together. Without it, the outer stars would fly off into space, the disk would unravel, and the entire spiral structure would disintegrate. The gravitational cohesion provided by the dark matter halo keeps the system intact, even as stars orbit at breakneck speeds. And yet, the story is more intricate. The unusual rotation of the bulge adds another layer to our understanding of how dark matter might be distributed. In many spiral galaxies, the bulge is thought to be relatively immune to dark matter influence because it forms early and is dominated by baryonic, normal, matter. But in NGC 7331, the fast-rotating bulge may be a sign that dark matter plays a more direct role in shaping the inner regions, or that the bulge itself formed in a unique way, perhaps through a rapid collapse of matter funneled inward, accelerated by the gravitational pull of dark matter. There's also a possibility that the angular momentum transferred during the galaxy's evolution was influenced by the dark matter halo. Dark matter doesn't just sit there, it interacts gravitationally with baryonic matter. During galaxy formation, gas collapses into the center of a dark matter halo, forms stars, and builds the visible components of a galaxy. The shape and density profile of the halo can determine how fast and how far that material collapses, which in turn affects the dynamics of the resulting galaxy. NGC 7331 is particularly useful for these studies because of its relative isolation. Without nearby massive companions tugging on it gravitationally, its structure and rotation are likely due to internal processes and the underlying dark matter framework, rather than external disturbances. This makes it a pristine case study, a clean sample in the cosmic laboratory. Furthermore, by studying galaxies like NGC 7331 at different radii, astronomers can test different dark matter density profiles. There's still active debate in cosmology about whether dark matter halos have cuspy centers, steep increases in density toward the middle, or chord centers with more uniform density. The way NGC 7331's inner and outer regions rotate provides key constraints on these models. If the inner bulge rotates faster than models predict under a cuspy profile, for instance, then perhaps the halo has a core, or perhaps the interaction between baryonic and dark matter is more complex than we thought. In a broader sense, galaxies like NGC 7331 help reinforce the cosmic ubiquity of dark matter. They're not outliers. Their behavior is consistent with what we see across the universe. The same dark matter signature appears in spiral galaxies big and small, near and far. It's the hidden glue of the cosmos, and NGC 7331's fast-spinning heart and steadfastly flat disk rotation are both fingerprints of its presence. The beauty of NGC 7331 is that it doesn't just confirm the existence of dark matter, it challenges us to refine our understanding of it. With each observation, each spectral line, each curve on a graph, we inch closer to uncovering the nature of this invisible substance that governs the fate of galaxies. And in the swift, silent motion of NGC 7331's stars, dark matter whispers its enduring influence across cosmic time. To the casual observer, a photograph of NGC 7331 might look like a snapshot frozen in time, a serene spiral galaxy suspended in space, its arms gracefully curving outward from a luminous core. But this tranquil appearance is an illusion. Beneath the calm exterior, NGC 7331 is a galaxy in motion, an immense dynamical system alive with activity on every scale, from the smallest swirl of dust to the grand orbits of stars and gas around its massive center. Like a city that never sleeps, the galaxy is constantly changing, spinning, and evolving, even if that change unfolds over millions and billions of years. At its most fundamental level, the galaxy's motion is governed by rotation. The disk of NGC 7331 is rotating at hundreds of kilometers per second, with stars and gas making enormous orbits around the galactic center. A single orbit might take hundreds of millions of years to complete. In that time, countless stars are born and die. The spiral arms, which might appear as static structures in telescope images, are actually density waves, regions of higher gravitational compression that move through the disk, sweeping up gas and triggering waves of star formation. These arms are not rigid objects. They are dynamic patterns that rotate with the galaxy, shaping its evolution. The spiral arms themselves are sites of intense motion and transformation. Within these arms, clouds of gas and dust are constantly collapsing under their own gravity to form new stars. These molecular clouds can span dozens or even hundreds of light years, and they are turbulent, chaotic regions where gravity, magnetic fields, and stellar winds interact in complex ways. As stars ignite, they begin to blow away the surrounding material with radiation and powerful winds, creating shockwaves that trigger more star formation nearby. This chain reaction ensures that the galaxy's arms remain dotted with brilliant clusters of young, hot stars, blue beacons of recent birth. But star formation is not the only type of motion occurring in NGC 7331. Older stars orbit the galactic center along more stable paths, tracing graceful arcs across the disk. Some of these stars have elliptical orbits, others more circular, and their velocities are influenced by the mass distribution of the galaxy, including the dark matter halo that envelopes it. These stars, though appearing still in images, are in fact racing around the core at tremendous speeds, locked in a gravitational ballet that stretches back billions of years. Meanwhile, the galaxy's central bulge, rotating at unexpectedly high velocities, adds its own layer of dynamic complexity. This region is densely packed with stars, most of them older and redder, but their rapid motion means the core of the galaxy is anything but static. Here, stars can interact more frequently, especially in the densest zones, and gravitational encounters can lead to the ejection of some stars or the capture of others by the central supermassive black hole. The high-speed rotation also suggests past episodes of gas inflow or merger events, which may have deposited angular momentum into the core and transformed its structure. Even the gas that fills NGC 7331 is in constant motion. Cold hydrogen gas, traced by radio observations, swirls throughout the disk, flowing along the spiral arms and occasionally falling into the center to feed star formation or even the central black hole. Warmer ionized gas glows in emission lines visible in optical wavelengths, revealing the turbulent effects of supernovae and massive stellar winds. These processes inject energy and momentum into the interstellar medium, stirring it like a pot and distributing newly forged elements from dying stars across the galaxy. In the halo surrounding the disk, there is motion as well. Though sparsely populated, the halo contains ancient stars and possibly the remnants of smaller galaxies that have been absorbed over time. These stars follow elongated, often chaotic orbits, and their presence serves as a fossil record of past accretion events. Streams of stars, trails left behind by disrupted satellites, might still be drifting through the halo, invisible in optical images but detectable through precise measurements of stellar motion and position. Motion in NGC 7331 isn't only internal. The galaxy itself is moving through the cosmic web, drifting along with the expansion of the universe. It travels within the local Hubble flow, receding from us at a velocity of approximately 800 to 1,000 km per second due to the expansion of space. Though we perceive it as a stable object in a fixed location in the sky, it is, in truth, hurtling away from us at enormous speed, its light taking over 40 million years to reach us. Over vast timescales, all of these motions contribute to the evolution of the galaxy. Stars orbiting through the disk experience gravitational torques that slowly shift their positions. Spiral arms wind tighter or unwind depending on the mass distribution. Star formation gradually depletes the gas reservoir, changing the overall appearance of the galaxy. The black hole in the center may feed on infalling matter, occasionally flaring in brightness. Even dark matter itself, though invisible, is constantly influencing the paths of every component in the galaxy. And this constant motion will continue into the far future. NGC 7331 is not currently interacting with other massive galaxies, but over billions of years, gravitational forces may bring it into contact with others. Minor mergers could disturb its disk, tilt its rotation axis, or trigger new waves of star formation. Over cosmic time, galaxies are never truly isolated. Their fate is shaped by both internal dynamics and external encounters, even if the current moment appears still. In every direction, NGC 7331 is in motion, stars tracing arcs through the night, gas coiling through arms, matter swirling toward the core. This unseen motion is what gives the galaxy life. It's not simply a collection of stars, but a living system, evolving and reshaping itself over time. The next time you look at an image of NGC 7331, remember, you're not looking at a moment frozen in space. You're gazing into a whirlpool of cosmic motion, a galactic dance that has been ongoing for billions of years and will continue for billions more. Long before modern observatories sent their gaze deep into the cosmos with radio waves, infrared detectors, or space-based instruments, the story of NGC 7331 began with nothing more than a telescope and a patient observer. The year was 1784, and the man behind the eyepiece was none other than William Herschel, a titan of early astronomy, known for discovering the planet Uranus just 3 years earlier. Scanning the skies from his observatory in England, Herschel swept across the constellation Pegasus and spotted what appeared to be a faint, nebulous smudge of light. This was NGC 7331, catalogued and noted long before anyone knew it was a spiral galaxy, let alone one with such structural similarity to our own Milky Way. At the time, the classification of such objects was still in its infancy. The concept of galaxies as distinct star systems beyond the Milky Way had not yet taken root. Objects like NGC 7331 were called nebulae, mysterious patches of light whose true nature wouldn't be understood until well into the 20th century. Herschel was diligent, noting the object's location and brightness, but he had no way of knowing that this faint smear in Pegasus would later be revealed as a sprawling spiral galaxy over 120,000 light-years wide. As telescopes improved over the following centuries, NGC 7331 continued to appear in star charts and deep sky catalogs. By the late 19th and early 20th centuries, photographic plates replaced visual sketches, allowing astronomers to preserve more detailed and objective records of the night sky. On these plates, NGC 7331 revealed hints of its spiral nature. It was still just a spiral nebula to most astronomers, as the debate over the true scale of the universe raged on. Was this object a cloud within our own galaxy, or was it an island universe, a separate galaxy in its own right? The answer came in the 1920s, thanks to Edwin Hubble's observations of Cepheid variable stars in the Andromeda Galaxy, which proved that these nebulae were far outside the Milky Way. While NGC 7331 was not the subject of those particular measurements, it became clear in the aftermath that it, too, must lie far beyond the borders of our home galaxy. The transformation from nebula to galaxy changed everything, and NGC 7331 became part of a much larger cosmic story, one that placed it some 40 million light-years away in the vast architecture of the universe. Throughout the mid-20th century, astronomers began studying NGC 7331 with increasingly sophisticated instruments. Long-exposure photographs taken through large ground-based telescopes unveiled its spiral arms, dusty lanes, and luminous bulge in far greater clarity. It was during this time that its resemblance to the Milky Way was first truly appreciated. While not identical, NGC 7331's unbarred structure, rich disk, and central bulge made it one of the best-known analogues to our own galaxy, an invaluable subject for comparative galactic anatomy. In the 1960s and 70s, with the rise of radio astronomy, researchers turned to NGC 7331 to map its hydrogen gas content. Observing the galaxy in the 21 cm hydrogen line allowed astronomers to chart its rotation curve, revealing, to their surprise, that the outer regions of the galaxy were spinning far faster than the visible mass could account for. This discrepancy provided yet another crucial data point in the growing case for dark matter. The same mysterious mass that Vera Rubin and her colleagues were discovering in other spirals appeared here, too. NGC 7331 was becoming a quiet participant in one of the greatest scientific revelations of the 20th century. With the launch of the Hubble Space Telescope in the 1990s, NGC 7331 became an even more detailed target of investigation. High-resolution imagery from space allowed astronomers to peer into the heart of the galaxy, uncovering its tightly wound core, the intricate structures of its spiral arms, and the brilliant blue knots of newborn stars in its dust lanes. These images transformed NGC 7331 from a blurry smudge into a fully realized galactic system, a cathedral of stars whose architecture we could now explore room by room. But Hubble wasn't alone. Infrared observatories like Spitzer, submillimeter telescopes, and millimeter wave arrays such as ALMA added even more layers to our understanding. These instruments pierced through the dusty veil of the galaxy's star-forming regions, revealing the warm cocoons where stars are born and tracing the flow of gas from the outer arms to the inner disk. The detection of polycyclic aromatic hydrocarbons, molecules associated with stellar nurseries, further highlighted the galaxy's active and complex life cycle. More recently, advanced integral field spectrographs have allowed astronomers to map the motions of stars and gas throughout NGC 7331 in exquisite detail. These instruments divide the galaxy's light into thousands of tiny spectra, pixel by pixel, giving scientists a three-dimensional map of its internal dynamics. From this data, the strange and rapid rotation of the central bulge was confirmed, a feature that continues to puzzle and inspire new models of galactic evolution. Even amateur astronomers have a role in the ongoing observation of NGC 7331. The galaxy remains one of the brightest and most beautiful spiral galaxies visible to small telescopes in the Northern Hemisphere. Positioned high in the autumn sky within the boundaries of Pegasus, it's a favorite target for deep sky observers. Under dark skies and with a good telescope, one can glimpse its elongated shape and central brightness, though the spiral structure remains just beyond visual reach. Still, the fact that it can be seen by the unaided eye, with assistance from a telescope, connects modern observers to Herschel's discovery centuries ago. NGC 7331's historical journey, from faint blur to detailed galactic twin, mirrors the history of astronomy itself. It's a testament to how far human curiosity and technology have come. Each new generation of instruments has peeled away another layer, uncovering structures, dynamics, and mysteries that weren't even dreamed of in Herschel's time. The galaxy's motion, its dark matter halo, its central bulge, and its stellar population all tell a story billions of years in the making, one we are only just beginning to understand. And even now, the story isn't complete. As new observatories like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope set their sights on galaxies like NGC 7331, there's every reason to believe that more secrets lie hidden within its starlit spiral. History may record what we've learned so far, but the galaxy's greatest revelations may still be waiting, shimmering quietly in the light that has traveled 40 million years to reach our eyes. In the field of astronomy, there exists a discipline that resembles a kind of cosmic forensics, an effort not to study what's happening now, but to piece together what has already happened. It's called galactic archaeology, and its practitioners are the universe's historians. They dig not through dust and bone, but through starlight, structure, and motion, seeking clues to reconstruct the vast and often violent histories of galaxies. NGC 7331 stands as one of the most valuable specimens in this field, offering a remarkably intact spiral structure, a mysterious bulge, and layers of stellar populations that serve as time capsules spanning billions of years. To understand NGC 7331 is to look into a galactic fossil bed, a record of birth, transformation, and endurance written in stars. One of the first goals in galactic archaeology is to establish a timeline. When did the galaxy form? How did its different components come into being? The bulge, the disk, the spiral arms. NGC 7331 provides an excellent laboratory for this kind of investigation because, like the Milky Way, it has a composite structure. It isn't just a homogeneous ball of stars. It has a halo of ancient stars, a thick and thin disk, and a central bulge that all formed at different stages. Each region contains stars of varying ages and compositions, and each can be used to trace a particular chapter of the galaxy's story. The halo of NGC 7331, like that of our own galaxy, likely formed first. The stars here are some of the oldest in the galaxy, low metallicity populations with little of the heavy elements created in later generations of stars. Their distribution and motion can indicate whether the halo formed rapidly in a single monolithic collapse or was built more gradually through the accretion of smaller satellite galaxies. In the case of NGC 7331, the halo appears to be relatively smooth, with some hints of asymmetries, perhaps remnants of minor mergers long since absorbed into the galactic structure. This supports the now widely accepted theory that galaxies grow hierarchically, through the cannibalism of smaller systems. Moving inward, the central bulge is of particular interest. In most spiral galaxies, bulges are either classical, formed in violent, early mergers, or pseudo-bulges, shaped more gently by internal processes over longer timescales. NGC 7331's bulge complicates this distinction. It rotates far faster than expected, which might suggest a pseudo-bulge formed through the secular evolution of the disk. But it also shows signs of an older, well-settled stellar population, hinting at a more complex origin. This has led astronomers to speculate that NGC 7331's bulge might be a hybrid, possibly the result of both ancient mergers and prolonged internal processes. Tracing the metallicity gradient, the change in chemical richness from the center outward, can help sort this out, since classical bulges tend to be metal-rich and uniformly old, while pseudo-bulges display more variety. The disk of NGC 7331 holds another set of vital clues. Its spiral arms, rich in star formation, point to an ongoing process of renewal and recycling. Here, stellar populations can be aged based on color, composition, and position. Young, hot, blue stars cluster along the spiral arms, often near nebulae and dense gas clouds, while older stars spread across the wider disk. By studying the distribution of different star clusters, astronomers can map how star formation has migrated across the galaxy over time. This migration is not random. It's guided by the gravitational dynamics of the spiral arms, the inflow of gas, and the interaction between stars and interstellar material. Over billions of years, these processes shape not only the visible structure of the galaxy but also its chemical enrichment, as stars forge heavy elements and return them to the interstellar medium through winds and supernovae. What makes NGC 7331 particularly intriguing is how undisturbed its disk appears. In many spiral galaxies, including the Milky Way, signs of recent mergers can be found in the form of warps, tidal streams, or disrupted spiral structure. NGC 7331, by contrast, maintains a clean, well-defined shape. This relative isolation suggests it has undergone a calm evolutionary history, punctuated perhaps by only minor mergers or smooth gas accretion. This stability allows astronomers to test models of internal evolution, how a galaxy can grow and change from within, without the jarring influence of major collisions. Yet, even without dramatic mergers, time leaves its mark. The presence of population gradients, variations in stellar age and metallicity across the galaxy, tells a story of gradual transformation. In NGC 7331, the inner regions tend to host older, redder stars with higher metallicities, while the outer disk contains younger, bluer stars and lower metallicity gas. This supports the theory of inside-out galaxy formation, in which the core of the galaxy forms first, with star formation gradually moving outward over time. Studying how steep or shallow these gradients are helps refine simulations of galaxy growth, allowing researchers to test different scenarios against observable data. Another layer of archaeological evidence comes from the dynamics of the stars themselves. By mapping their orbits, velocities, and dispersions, astronomers can reconstruct the gravitational history of the galaxy. In NGC 7331, the transition between the rapidly rotating bulge and the more moderately spinning disk provides a key region of interest. Analyzing how stars move between these zones can shed light on how angular momentum has been transferred across the galaxy, either through internal resonances or as a result of long-past interactions. And then there are the globular clusters. These dense, spherical groups of stars are among the oldest structures in a galaxy and serve as reliable tracers of its early formation. NGC 7331 is known to host a significant population of globular clusters, scattered in its halo and outer regions. By studying their spatial distribution, motion, and metallicity, astronomers can gain insight into the conditions under which the galaxy assembled. Were these clusters formed in situ, in the early burst of star formation that built the galaxy's core? Or were they accreted, captured from smaller galaxies that ventured too close? Their properties act like archaeological relics, preserving the memory of ancient cosmic events. Even the gas in NGC 7331 contributes to this reconstruction. Cold hydrogen detected through radio observations outlines the supply lines of galactic growth, how the galaxy continues to draw in material from its surroundings, feeding new generations of stars. Chemical signatures in this gas reveal whether it has been recycled many times through stars, or if it represents pristine material from the intergalactic medium. The relative abundance of certain elements, like oxygen and nitrogen, can tell astronomers how long gas has been processed in the galactic ecosystem and how efficiently star formation has occurred throughout the galaxy's life. Altogether, the archaeological study of NGC 7331 reveals a galaxy that is ancient yet active, stable yet dynamic. Its story is one of gradual assembly, internal refinement, and quiet endurance. Unlike galaxies torn apart by recent collisions or warped by strong gravitational interactions, NGC 7331 offers a more controlled environment to study the natural, unhurried evolution of a spiral galaxy. By analyzing its structure, stellar populations, motion, and chemical makeup, astronomers can reverse engineer billions of years of history, tracing how matter came together to build this majestic spiral in the sky. In essence, NGC 7331 is not just a galaxy, it is a timeline, stretched across 120,000 light-years, carrying in its stars and gas the imprint of everything it has seen and survived. Through the lens of galactic archaeology, we are not simply observing light from a distant galaxy. We are reading the story of how galaxies, including our own, came to be. When we gaze upon NGC 7331 through our telescopes, we are not merely witnessing a beautiful spiral galaxy. What we're truly seeing is a cosmic mirror, one that reflects not only the structure of the Milky Way but also possible chapters of our own galaxy story. Because we are embedded within the Milky Way, we cannot view it from the outside. We see our galaxy edge on, from within, our view obstructed by thick dust lanes and complicated by our position in one of its arms. But with NGC 7331, we are given the rare opportunity to observe something remarkably similar to ourselves, from the outside looking in. This idea, that NGC 7331 serves as a proxy for our galaxy, has fascinated astronomers for decades. In terms of mass, structure, and morphology, the two are alike. NGC 7331 is slightly larger, and it lacks the central bar that defines the Milky Way, but its spiral arms, central bulge, and overall dynamics provide a close enough match to make it a valuable analog. By studying it, we can speculate about what our own galaxy might look like if we could fly beyond it and look back, a glorious swirl of starlight, dust, and gas spinning in the black of space. But this mirror does more than satisfy curiosity. It becomes a scientific tool. When we observe the populations of stars in NGC 7331, how they're distributed, how they orbit, how they vary in age and color, we gain insight into how similar populations behave in the Milky Way. The visible patterns in NGC 7331's disk may reveal patterns hidden behind dust in our own. The swirling molecular clouds, active star-forming regions, and luminous clusters all serve as comparative reference points, helping us infer what we might never be able to see directly. More than that, NGC 7331 may be a window into our past. The light we receive from it today left the galaxy some 40 million years ago. This means every photon we collect, whether in visible, infrared, or radio wavelengths, carries information frozen in time, an image of the galaxy as it was when dinosaurs still roamed Earth. In this way, looking at NGC 7331 is akin to time travel. And since spiral galaxies evolve slowly over cosmic timescales, it's not unreasonable to suggest that some features of NGC 7331 in that moment might resemble what the Milky Way looked like tens of millions of years ago. Yet this mirror may also show us what lies ahead. Its central bulge rotates faster than our own, hinting at an evolutionary path that diverged at some point. Could the Milky Way's bulge one day undergo a similar acceleration under the influence of internal dynamics or minor mergers? Could the gas-rich spiral arms of NGC 7331 be a preview of how our galaxy might continue to form stars long into the future, given the right reserves of fuel? The isolated nature of NGC 7331 may also show us what the Milky Way might have become had it not formed in such a crowded neighborhood. The Milky Way exists in a bustling environment, with satellite galaxies like the Magellanic Clouds and the upcoming collision with Andromeda looming on the horizon. In contrast, NGC 7331 resides in a more peaceful part of the universe, with its apparent companions, NGC 7335, 7336, 7337, and 7340, being only line-of-sight alignments rather than true members of a gravitationally bound group. This quieter existence may have allowed NGC 7331 to retain a clean spiral structure, undisturbed by major interactions, which makes it all the more useful as a control sample for understanding unperturbed galactic evolution. In another sense, NGC 7331 reveals what the Milky Way could be lacking. The absence of a central bar in NGC 7331, for instance, presents an interesting contrast. Bars in galaxies are believed to play a key role in funneling gas into the core, fueling both star formation and supermassive black hole activity. The Milky Way's own bar may be responsible for shaping its central region in ways that NGC 7331 avoids. This comparison leads us to wonder how much of our galaxy's internal evolution has been dictated by the presence of its bar, and what might be different if that structure had never formed. As we explore NGC 7331 in increasing detail, mapping its gas dynamics, tracing its metallicity gradients, and modeling the orbits of its stars, we are not simply studying an object far away. We are building a bridge of inference that helps us understand the hidden regions of our own home. When data from the James Webb Space Telescope or large ground-based surveys target NGC 7331, those results echo back toward us, reshaping our assumptions and refining our models of the Milky Way. Even visually, in high-resolution composite images, NGC 7331 gives us a hauntingly tangible picture of our place in the universe. It's humbling to look at that galaxy and realize, if a being were living in NGC 7331 and pointing its telescopes toward us, they would see the Milky Way in much the same way. A swirl of stars. A collection of glowing gas clouds. A quietly spinning structure, rich in motion, yet suspended in the void. And they would be just as unable to see it from within as we are, forced, like us, to rely on analogs and proxies to understand their cosmic neighborhood. So NGC 7331 is not just a spiral galaxy in Pegasus. It is a cosmic echo, a near-twin reflecting both where we came from and where we might be going. Through its light, we trace the arc of our own galaxy's life, a majestic, spiraling biography written not in words, but in gravity and light. Despite all that we've learned about NGC 7331, its spiral arms, its dust lanes, its ancient halo and star-forming regions, one feature still defies complete explanation: its fast-spinning central bulge. This unexpected dynamic behavior, at the heart of an otherwise orderly spiral galaxy, represents one of the most intriguing unresolved mysteries in modern galactic astronomy. While most central bulges in spiral galaxies rotate slowly and behave like spheroidal, pressure-supported systems, NGC 7331's bulge defies that trend. It spins more like a disk, rapidly, dynamically, and with a coherence that raises more questions than it answers. Why does this happen? The first step in confronting this puzzle is to look at what bulges are supposed to be. In the classical model, bulges are thought to form early in a galaxy's history, either through major mergers or rapid collapses of gas clouds. They are pressure-supported, meaning their structure is held up not by rotation, like a disk, but by the random motions of their stars. They typically appear spherical or elliptical in shape, filled with older, redder stars, and they often contain little gas or dust. In contrast, disks are rotation-supported and flatter, with more organized movement and active star formation. NGC 7331's bulge doesn't fully conform to either classification. Though it appears like a classical bulge in terms of brightness and size, its rotation is too fast, more like what we'd expect from a disk. This has led astronomers to question whether it might actually be a pseudobulge or some hybrid form. Pseudobulges arise through secular processes, not violent mergers. They form gradually as gas and stars migrate inward due to the torques of bars and spiral arms. But this leads to another problem. NGC 7331 doesn't have a bar. Without a bar to channel material inward, what mechanism could have built such a rapidly rotating bulge? One possibility is that NGC 7331 experienced past mergers with smaller galaxies, not large enough to disrupt its spiral structure but sufficient to inject angular momentum into the central regions. In such a scenario, the stellar material from an accreted satellite could have deposited a significant amount of rotational energy into the core, spinning it up over time. Yet if that were the case, we might expect to see other signs of disruption, stellar streams, disk warps, or anomalies in the outer halo. So far, observations haven't revealed clear evidence of such features, though it's possible they've already dissipated or remain hidden. Another hypothesis involves gas inflow and internal instabilities. In this view, even in the absence of a bar, spiral density waves or other non-axisymmetric features in the disk could slowly drive gas toward the center over billions of years. This inflow could settle into a rotating structure and form stars, effectively building a fast-spinning bulge from the inside out. If this process occurred early and was sustained, it might account for the rotational properties we now observe. However, The level of rotation in NGC 7331's bulge appears extreme, even for pseudobulges, suggesting that something more than secular evolution might be at play. There's also the tantalizing role of the central supermassive black hole. If NGC 7331 harbors a massive black hole, as many galaxies of its type do, it could influence the rotation of stars and gas in its vicinity. Feedback from black hole activity, outflows, jets, or even subtle gravitational effects might contribute to shaping the bulge's dynamics. But once again, the influence of the black hole would typically be confined to the very central regions. The observed rapid rotation spans a wider portion of the bulge, suggesting a more systemic origin. Complicating the issue further is the lack of a simple correlation between bulge rotation and other galactic properties. In studies of other spiral galaxies, fast bulges are rare. Some exist, but they're often tied to bars or recent interactions. NGC 7331 seems to be an outlier, a galaxy that should be well behaved, yet isn't. Its fast bulge makes it a key data point in refining our models of galaxy formation and bulge evolution. It resists easy classification, sitting between categories and hinting at a diversity of galactic pathways that may not be well captured by current simulations. To get to the root of the mystery, astronomers are turning to high-resolution integral field spectroscopy, which allows them to map the motions of stars and gas across the bulge in fine detail. By combining this data with stellar population analysis, looking at the ages and metallicities of the stars, they hope to determine whether the bulge formed quickly or slowly, from internal processes or external accretion. So far, results suggest a mix. The bulge contains both old and intermediate-age stars, some of which formed in rapid bursts, others in more prolonged episodes of star formation. This diversity supports the idea that multiple mechanisms may have shaped it. There's also ongoing work using galactic simulations to test different evolutionary histories that could give rise to such a feature. Some simulations show that misaligned infall, where gas accretes into the galaxy at an angle to the existing disk, can lead to unusual bulge dynamics. Others point to the long-term influence of spiral arm resonances or transient internal features that could redistribute angular momentum. Yet no single scenario has yet matched all the observed properties of NGC 7331, keeping the question open. And so, the mystery endures. Why does NGC 7331's bulge spin so fast? What forces acted upon it, subtle or violent, internal or external, to produce such a unique signature in its core? These questions remain not just a curiosity, but a challenge to the foundations of galactic theory. In solving this riddle, we don't just learn more about one galaxy, we sharpen our understanding of the entire spiral galaxy family, including our own. Until we have a clearer answer, NGC 7331 stands as a monument to what we don't yet know, a reminder that even among the most familiar-looking cosmic structures, surprises still await. Beneath its graceful arms and glowing core, it harbors a secret encoded in stellar motion, a signature of a past we have yet to fully decode. In the great cosmic ocean, where galaxies drift like glowing islands of time and gravity, NGC 7331 is a rare kind of beacon. It doesn't dazzle with bizarre distortions or blaze with the chaotic fire of colliding giants. Instead, its mystery lies in its quiet resemblance, its haunting similarity to the Milky Way. But as we've explored, that resemblance is only surface deep. Beneath its spiral elegance lies a galaxy that twists expectations, confounds models, and invites us to look deeper. NGC 7331 is not just another spiral galaxy. It is a cosmic twin with a twist, and in that twist, it teaches us one of the most profound lessons of modern astronomy: even the familiar holds unknowns. Throughout our journey across this galaxy, we've traveled from its dusty, star-forming arms to the silent halo of ancient stars. We've descended into its unusually fast-spinning bulge and emerged with more questions than answers. It has revealed to us a rich, rotating canvas, a laboratory of star birth, death, and evolution. And all the while, it has mirrored back to us a picture of home, not exact, not identical, but achingly close enough to spark reflection. In NGC 7331, We see what the Milky Way might have looked like from the outside 40 million years ago. We see what it might look like today, if only we could escape its confines and gaze back. We see a benchmark, a control in the grand experiment of understanding galactic evolution. But perhaps most importantly, we see a reminder of perspective. Because we can't see our own galaxy from afar, galaxies like NGC 7331 become our eyes, our guides. They are the cosmic mirrors that allow us to study ourselves through the reflection of another. And that reflection is not static. NGC 7331 is not frozen in time. It is alive with movement, its stars orbiting, its gas swirling, its arms continuing the ageless rhythm of gravitational dance. New stars are born as old ones fade. Molecular clouds collapse while black holes sleep or stir. Like all galaxies, NGC 7331 is an organism made of light and gravity, time and transformation. Its past is etched in starlight, its future unwritten but slowly unfolding with every rotation. And yet, despite all we've learned, it keeps secrets. That central bulge, why does it rotate so quickly? Was it born in calm or chaos? Was it shaped by collisions long forgotten or by processes we don't yet understand? The answers to these questions don't just belong to NGC 7331, they reverberate across all of galactic science. They force us to confront the gaps in our models, the limitations in our theories, and the endless curiosity that drives us forward. In a universe of extremes, of colliding clusters and ravenous black holes, NGC 7331 might seem tame. But its lesson is subtle and profound. It whispers, rather than shouts, showing us that the most powerful truths often come not from the outliers, but from the things that seem familiar, until they surprise us. Its quiet defiance of galactic norms is not a fluke. It is a challenge. It urges us to look again, to question assumptions, and to embrace the unknown. Because in the end, the cosmos is not just a place of wonders, it's a place of questions. Every galaxy is a chapter, every star a sentence, and every unanswered rotation a mystery still waiting to be read. NGC 7331 is one of the most elegant chapters we've found, a galaxy that tells our story while holding one of its own. It is a twin not in name, but in spirit. A sibling in the spiral family. A reminder that we are not alone, and that in the quiet whirls of distant light, we might glimpse not only what we are, but what we have yet to become. So the next time you look up at the constellation Pegasus, know that far beyond those stars lies a spiral galaxy, 40 million light-years away, spinning in silence. Know that we've seen its light, measured its motion, and traced its arms like cartographers of time. And know that in that light, drifting across the cosmos for tens of millions of years, there's a message, that the universe is deeper than what we see, and more mysterious than what we know. And even a galaxy that looks like ours can still rewrite the rules. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.